Hey, how's it going? Pretty well. Sorry, I have to full play for you. I'll let you know if you go 5 minutes. I'll say you lose 35 or 30 or questions. So 5 for questions, so 35 plus 5. Okay. All right, so welcome to the afternoon session. Our first speaker is Yves Bultinck. Hopefully you didn't butcher your name too much.
Okay, well, first of all, can you all hear me working?
Not very well.
Not very well? I'll put it closer then. Better? No?
Should be better.
Better? Okay, good. Okay, well, first of all, let me thank the organizers, of course, for putting together this very nice workshop. And also for giving me the opportunity to speak here about some as of yet unpublished work. So my talk today it's a slight change of topic because what I will be talking about today is motivated by the Cuprate superconductors. And actually, I will be talking about the electron-doped cuprates. So usually people are more focused on the hole-doped side because the physics seems to be richer, GC is higher. But there is some evidence that also on the electron-doped side, some very interesting things are going on. And so, well, we can first look at this cartoon of the phase diagram as a function of electron doping and temperature. So at small doping, we have the antiferromagnets, which now actually extends to much larger doping values than in the on the hole dope side. And this AFM actually overlaps with the superconductor. So there's a region where there's actually coexistence of superconductivity and antiferromagnetism. And then on the overdoped side, there's some things that people cautiously also call a strange metal, something that doesn't really look like a Fermi liquid. But then if you dope enough, then you recover the standard Fermi liquid behavior. But in this talk, I will actually be mostly interested in this purple shaded region, which is what people also in an analogy to the hole dope side, again, with caution, call a pseudo gap. And in this region of the phase diagram, there are antiferromagnetic fluctuations. But as you cool down the system, there seems to be no long range or static antiferromagnetic order that really develops at these doping values. But nonetheless, people see a Fermi surface which is reconstructed. It does not look like the large Fermi surface of the non-interacting electrons. And so this means that, okay, at least at zero temperature, if you want to get such a reconstructed Fermi surface without there actually being some form of symmetry breaking, this means that you need some topological order because you need to violate the Luttinger constraint. And so I will be starting from a theory which has this topological order and which we think is a potential candidate to describe this pseudo gap region. But actually the main question, because that theory itself will not be new, that actually has been studied before in the literature. But the new thing is that we will ask, well, let's assume you start indeed in that particular pseudo gap. How would you get from there into the superconductor as you cool down your system? So the main question I want to address, like I want to know how to think about this, what's happening, what is how is the pairing arising in this system? Okay. So one reason why people are less focused on the electron-doped side is that it actually seems conceptually easier in the sense that people have more the feeling that they actually understand what is going on there. I don't know if that's true, but people at least think they understand better what's going on there. And that's because it seems like really all there is antiferromagnetic fluctuations. There's no stripes, no charge density waves, no other competing orders. So it seems like the antiferromagnetic order, the antiferromagnetic fluctuation, they are the only game in town. And so we will therefore start from an effective theory which has exactly these antiferrometric fluctuations and couple them to fermions which have a Fermi surface. And so, okay, we start from an effective action, which consists of two parts. First, we have just a bosonic part. It describes space-time fluctuations of this unit vector field n. And this is just, these are the antiferrometric, the directional fluctuations of the antiferrometric order. And then these fluctuations, or these this vector field, is coupled to the fermions. And the fermions, they have a nearest neighbor hopping term, and also a next nearest neighbor hopping term. Obviously, a chemical potential, and then their spin. So the spin of these fermions couples to this this unit vector field. And note that this the coupling is staggered, so it has a different sign on each of the two sublattices, and that's because ferromagnetic order of the bosons then becomes antiferromagnetic order for the fermions, as it should in an effective theory for the cuprates. Good, so that's the starting point. And if you just stare at this action and you want to figure out, well, how does actually translation symmetry act on my degrees of freedom? Well, you see it actually acts in the usual way on the fermion operators. You just take a fermion creation or annihilation operator and shift it by one lattice side. But if you look at how translation acts on this this unit vector field, you find that actually to leave this action invariant, you not only have to translate it, but you also have to provide an additional minus sign. And that's because of this staggered nature of the coupling. And I put this in a red box because it's important. I mean, basically everything, all my results ultimately follow from this fact here, from this somewhat unusual action of translation on my my vector field n. Okay, and like I said, I will start from the hypothesis that to understand this pseudo gap in the electron-doped cuprates, or this Fermi surface reconstruction without symmetry breaking, you do really need to think in terms of a fractionalized theory. And so to introduce a fractionalization, starting from the spin fermion model, I will fractionalize first my my vector field n. And then I will just express this vector field in terms of a spin-on field z through this vector of Pauli matrices. And so z has spin 1/2, but it also carries a U1 gauge charge. Because this decomposition, it's not unique. There's obviously a phase freedom, so I can multiply the spin-on field with an arbitrary phase, and since I have z and z star, well, that phase would always cancel, and so this phase can even depend non-trivially on space and time. So that's really a gauge freedom, of a gauge symmetry, of a gauge redundancy of this parameterization. Okay. And again, there's a red box because translation acts non-trivially on these spin-on degrees of freedom. In particular, because of that minus sign that the vector field had to acquire under the translation, you find that the spin-ons actually have to, well, translation acts by, well, just translating them, and then also doing a Kramer's time reversal symmetry. And that's because you have to translate, and then the Kramer's time reversal flips the direction of the spin 1/2 degrees of freedom. And that then implies that the vector field, which is composed of these spin 1/2 degrees of freedom, then also picks up the necessary minus sign. And so what this means is that this action of translation actually flips the gauge charge, because z goes to z star, and if z has, let's say, by convention, gauge charge +1, then z star has gauge charge, the U1 gauge charge -1. And so this is important. So this will have, again, this will determine basically my main, the form of my main results.
Question.
Yeah.
Is already a choice of a projective symmetry group? Because I could imagine that you have many choices at the gauge level how to implement the symmetry while still having the same physical symmetry implementation.
You mean, yeah, sure, indeed. There is a gauge, there's also gauge symmetry. So I could combine this with an arbitrary action of the gauge symmetry. I don't know if that's what you mean.
Like there are, gauge inequivalent projective symmetry groups, right? They will give
Yes.
different kind of spin liquids.
Yes, I think here, there's no other way to flip the direction of n than to do the Kramer's time reversal, I think. And this, yeah. So modulo gauge transformations, I think this is unique.
Okay.
Yeah.
I'm a bit confused by your previous. So you have your C fermions, and all you know is that they're Hamiltonian. When you go to the next Brillouin zone, the eigenvalues have to be the same, but you have a freedom of how you want your fermions to transform. You can do a gauge transformation on those. So I don't understand this minus sign, because it seems that I could just reabsorb by changing the gauge I chose to transform my operators when I go there.
Right, but I think the C electrons, as of now, they are really microscopic fermions. They don't carry a gauge charge. So for them, I somehow, I have to use the normal action.
But they came from diagonalizing a Hamiltonian, right? They are the eigenstates of your system, right?
Oh, sorry, what Hamiltonian is like some apinio?
I know, you must start with some Hamiltonian, right? You had you're in a band basis, I'm saying, right?
No, not here. This is just local hopping, just electrons hopping on a square lattice. No?
You just said one orbital, so the band basis is the.
Sure. Well, yeah. Okay, the orbital basis is the band basis. That's right. Yes.
Basis, and you have an antiferromagnet.
Yes, exactly. Yes, indeed.
In some language.
Yeah. Okay. Yeah.
Is your translation a unitary symmetry?
So is what?
Is your translation a unitary symmetry?
Yes, originally it is, but when I split it, becomes a product of two anti on each of the z's. So it is actually I think the way it works here. Well, actually, from now on everything will be real, so it doesn't matter. But indeed here, the way I define it here, it's as an anti-unitary symmetry. It has to flip the spin direction.
Seems all right.
Okay.
The word has to means what?
Sorry?
The word I have to do it means what?
If you want to, you have to figure out how does Z need to transform such that N becomes minus N. You have to figure out what is the action I have to do on Z to give N a minus sign. Yeah. Okay. Good. Any other questions at this point? Good. And then using these, these phenon degrees of freedom, I can just define this 2x2 matrix R. And it's not hard to check that this is an SU2 matrix. Okay. So I'm going to use that matrix now to define the fermions which do have gauge charge. So these are the psi's. And I just rotate the spin of my microscopic fermions with that 2x2 matrix R. Okay, good. I can do it for the psi bar and the psi, obviously related in this way. So remember, I had two electrons spin, two microscopic electrons spin up, spin down. After this rotation, I get two psi's. I call it psi plus and psi minus, because if you write it out, you find that this is just contract the spin indices of Z with the spin indices of C dagger or C bar in the path integral. And then C minus is contract C bar with this combination. And so the plus and minus refer to the gauge charge, because by convention, I say that Z has gauge charge +1 and Z star has -1. So these have opposite gauge charge. And so these are fermions which, like I said, have a U1 gauge charge, but they are spin singlet because the spin indices between the spinon and the microscopic fermion are contracted. So this is now a spin, these are spin singlet objects. And so they satisfy the standard definition of a charge on excitation or degree of freedom.
Sorry, I want to get back to the question about unitarity. So acting on I,
Yes.
translations and the 2 minus I.
Here, I think, only I that the I in the sigma Y. That will, but that's the only I in the problem. Yes.
So if my hoppings are complex, or if I add a term to the Hamiltonian, how do I know how to transform?
I would have to think about exactly how I would have to let it act, but probably I don't want to touch those other imaginary numbers. Yeah. Yeah.
Seems more like a unitary particle hole symmetry rather than a non-unitary time reversal.
A particle, yeah, okay. If you decompose Z into the modes, the annihilation equation operators, it is indeed a particle hole transformation. That's true. Yes.
Then it can be unitary, even though it takes Z as far.
That's true. Yes. But the reason is okay. I would have to think about this, but the reason that I have to think about this is that there's no other imaginary numbers in my theory, so I never had to think about exactly how it acts on these potential other imaginary numbers. Okay. Good. So we have now, I defined these psi's, psi plus, psi minus, and what's the physical meaning? Well, I just rotated the spin of my macroscopic fermions to align with the direction of n. So the C, my macroscopic electrons, they see some potentially completely disordered vector field n, but then the psi's, they actually just see a uniform or an ordered or a static configuration of n. And that's because I chose these R matrices to satisfy this property. So they kind of rotate n dot Pauli matrices into just sigma z. Okay, I should also mention that this way of introducing fractionalization and charge-ons has a very long history, especially in the context of high TC. Goes back to the early days. Schreiman and Sigia did this, Schulz, and okay, was followed by many people. So this is by no means a new way of introducing fractionalization. And these people also basically figured out how to, well, it's not very hard, but they already did it, how to exactly rewrite your action in terms of these other degrees of freedom. So in terms of the psi's, the z's, and then some gauge field, I will get to that. But the first thing to note is that because of this rotating reference frame, this, what used to be the coupling between the microscopic fermions and the vector field now actually becomes a static term, because you kind of have absorbed these fluctuations in the psi's, and for the psi's, this coupling becomes a static staggered potential. And so this implies that the charge-ons, these psi's, if you just look at the free dispersion of these degrees of freedom, they are gapped. So this dispersion has a gap at half filling. Also note that this seems to violate the translation symmetry, but it actually does not, because, well, remember, translation flips gauge charges. So you translate, you pick up a minus sign from the staggered, well, this term, these minus signs here, but then you also flip the gauge charges. So there's a sigma x here, which anti-commutes with the sigma z. And so that gives you a second minus sign. And so this term is really, it does really respect the translation symmetry. Okay. And then these charge-ons, like I said, they have a gauge charge. This U1 gauge symmetry is really redundancy of my choice of parameterizing the theory. So my action should be gauge invariant. And it is because these psi's coupled to this gauge field. So this is the temporal component of the gauge field. You can write it in this way in terms of the spin-on fields. And then there's also the spatial components, which you can again express in terms of the z's. So these are minimal coupling terms between the charge-ons and this U1 gauge field. Okay, and then there's also, if you exactly write your action, you also find that there's a second term in the action. These terms were also found, again, in the early days of high TC by Schreiman and Sigia. So I will not dwell on these any further. They are important. They lift some degeneracies. So we do take them into account, but for the high-level analysis that I will be giving in this talk, they are not very important. So we do take them into account, but I will actually not come back to these terms. Okay. And then what you see if you rewrite your action in terms of these charge-on, spin-on, and U1 gauge fields, as you find actually that this gauge field has no bare kinetic term in the action. So all its dynamics is generated by coupling to the spin-ons and charge-ons. And so we will now assume that the spin-on mass is much smaller than the charge-on mass. And then the dominant contribution to the dynamical term for the gauge field will come from the polarization of the spin-on degrees of freedom. And so we will use the standard one loop, the paramagnetic diamagnetic contribution to the polarization from the spin-ons to get a dynamical term for our gauge field. And to calculate this polarization, here we use some continuum approximation, because if we use this continuum expression for a nonlinear sigma model, then it's well known how to just exactly rewrite this in terms of the gauge field and the spinon field. So you can use this expression and get some results for these polarization, these one-loop polarization diagrams, and use that to get some idea for what the dynamics of that gauge field will be. And in particular, how it will depend on the parameters in your theory. Okay. So let's now imagine that we started half filling. So I told you that, okay, the charge-ons are gapped. I assume my system, because I want to describe the pseudo-gap, there's no actual antiferrometric order. So spinful excitations are gapped, so the spinons are also gapped. There's no condensation of the spinon. It's a gapped excitation in this theory. So at half filling, everything is gapped besides the photon fluctuations of the U1 gauge fields. And let's now imagine that we inject a single electron on top of this, into this insulating state. So really, in this description, that introduces a pair of particles. It introduces both a charge-on and a spinon. And these two particles, they interact strongly via this U1 gauge field. And so the first thing we want to do is we want to have some idea of, what are the bound states that are now formed between these two particles? Because this interaction is really strong. At long distances, you find, the Coulomb interaction is logarithmic. So it's a very strong interaction. So we really do expect that there will be bound states. And so here, there's multiple ways to approach this problem. We just try the simplest thing. So we say, okay, let's look at the Fourier components. Then I have the spinon and anti-spinon creation and annihilation operators. So these are the normal modes of my spinon field, my complex fields. And then to get some idea of what the bound states are, we have to make some approximations. And so what we do is we say, okay, let's work in the Coulomb gauge. That's not an approximation. You can use any gauge you want. But then the first approximation is, we know the Coulomb interaction is pretty strong. So let's only first look at the density interaction mediated by the temporal component of the gauge field in the Coulomb gauge. That gives you the Coulomb interaction. And let's just ignore the current interactions for now. And then also what we want to do is we actually want to turn this into a Hamiltonian problem. So really, I think you already know where I want to go. I want to turn this into a Hamiltonian problem where I just have a pair of particles interacting with some static potential.
Sorry to interrupt. What about bound state of spinons by themselves?
If I inject a single electron, I inject just one spinon and one charge-on.
And
that can be dressing, but that we will ignore. There can be dressing of other spinon pairs, but this level of approximation, you don't see that.
But if you want to have a spinon description of antiferromagnet, then we know that at the disordered antiferromagnet, we know that at the end of the day, spinons form bound states. So you have poles instead of branch cuts.
Yes, I agree.
So where is this physics here?
But that's when you excite the system and you inject a pair of spinons, and then these will. But that's a different bound state problem. We just assume that we will work in the gauge the charge neutral sector, and then just excite a pair of spinons. Here we just say let's go to the sector where we have added one electron, and then look at just the bound state problem for the spinon and charge, and that's one electron introduces. Yeah. Okay. Good. So like I said, so the reason we do these approximations is because if we do this, then we get a Hamiltonian for a pair of particles interacting with some static potential. And then, of course, you can do, this is very easy to do numerically. You can solve the two-particle quantum mechanical problem numerically, just get the bound states spectrum. But before I actually show the numerical results, let me just walk you through this well, this rather lengthy formula. And the reason I'm showing it is that this is really, well, everything really follows from this equation. And what I write here is basically, well, F dagger, I call the creation operator for one of these bound states. And it consists of pairs of particles. So you see here different terms, each of which has a charge on and then spin-on or anti-spin-on. And these are all the gauge invariant combinations. And these alphas here, they are the wave function coefficients in momentum space. So they are they represent the bound state wave function. So you have the alpha and you have the beta. And so this form of the bound state wave function is fixed by the symmetries of the problem. And so let's focus on translation and the U1 gauge symmetry. So like I said, the fact that we have only these combinations because we need to have a gauge neutral object. And then this is the most general expression for a bound state wave function that has a well-defined momentum q. So if I act with the translation, I get e to the iq dot, well, a. And so let's first look at these, well, these first two terms. So what you see here is, well, the momenta of the two particles, they add up to q, so the small q. So each of these terms by themselves, well, have the same momentum as the momentum I used to label my bound state itself. And then remember that, again, translation flips the gauge charges. So translation would also interchange these two terms, but they come with the same coefficients alpha. So that ensures indeed that this combination of the two terms is indeed translation invariant. Now for these other two terms, yeah. Oh, wow. Okay.
-2, actually.
Oh, okay. I have to go a bit faster then. With the other two, you see that actually the total momenta of the particles does not add up to small q. It actually adds up to small q plus big Q, and big Q is the AFM vectors. It's pi. If you would just do the normal translation, this would actually not give you e to the iq dot a, it would give you minus e to the iq dot a because of this shift by the AFM wave vector. So, but that other minus sign actually gets cancelled because, again, translation flips gauge charges. So it actually interchanges those two terms. They come with a relative minus sign. So flipping them gives you another minus sign. And that cancels with the minus sign you get from the shift by the AFM wave vector. So these are the general bound states which have a well-defined momentum under the translation operator. Okay, and these are then the numerical results. So you can just calculate, well, just do two particle ED, and we will focus on the pink band here because that's the band where electrons, where a single electron on top of the half-filled state would go into. And so if you make a 2D color plot of the dispersion of that pink band, you find this result. So these are the parameters I used, by the way. And the first good news is that the minima are at the x points, and that's good because these are at the same location of a weakly doped AFM, and so you would get pockets, you would get electron pockets at the same location as where they seem to be from experiments on the electron doped Cuprates. Okay, so that's good. Okay, so here's some other results. So this is to give you an idea of the spatial extent of the bound state wave function. So this is for, well, a representative value of Q, representative value of the momentum of the bound state, and along a cut at x is 0 and along y. So you see they extend up to like maybe 2-3 sites. And then here is some proxy for the spectral weight. You see at some with some chemical potential value, you see these pockets, and indeed they're somewhat brighter towards the M point and fainter towards the gamma point. Also, that seems to agree with some RPS. But okay, what I really want to get to is, now let's imagine we don't just inject a single electron, but we inject a small density of electrons on top of the half-filled state. So I will make the approximation, which I think should become exact in the dilute limit, where I would just take these bound states to be rigid. So as long as the separation between the two particles in a bound state is much smaller than the average separation between the bound states themselves, I can just assume that these bound states will be identical to the ones or that I found for just the two particle problem or the one electron problem. And of course, yeah, sorry.
Sorry, you showed previous slide with Fermi surface, with popular. This will have feeling as far as I understand.
No,
But
sorry.
this
Here,
point-
this is for illustrative purposes. We just already assumed that we've introduced a finite density, just to have an idea of how does a spectral wave.
Then you said, let's go to finite code.
Yeah, so this is already just doing what I just
Right,
explained. Yeah. This is just to give you an idea of what's the effect of the matrix elements on the spectral weight. Where is it brighter? Where is it weaker? Okay, and of course you already know what I want to do. I just in the AMO way of thinking, I just want to figure out, okay, what's now the interaction between just two of these bound states? How do they feel each other's presence? And okay, we know they're composed of pairs of oppositely charged particles. And okay, these particles, they will interact. There's two particles in each bound state. So we have 4 interactions, 2 repulsive, 2 attractive. And then the question is, what is the combined effect of these 4 types of interactions? And so I will project these this combination of 4 interactions into that pink band, so into that band of the bound states. And you get an interaction of this form. It's a very general expression. So the main question is, what is this V, Q1, Q2, Q? And you find you can write it like this. First of all, there's this potential, this Fourier transform potential, V of Q. And what you find is that it's the inverse of the polarization. So the inverse of the static gauge field propagator, the A naught, the temporal component of it at least. But it's actually not that exactly the polarization. It's that polarization shifted by capital Q. So this is peaked not at 0 momentum. This is peaked at the antiferromagnetic wave vector. And that's maybe I can explain a bit why that is by looking at these other 2 contributions to the matrix elements of the interaction, which are these form factors lambda. And again, a lengthy expression. You don't need to absorb all the details. But the reason I'm showing it is that I want you to notice that this form factor is just some difference of the alphas contracted with beta and some difference of the betas contracted with alpha. So there's some, we only have cross terms. We only have overlaps between the alpha part of the bound state wave function and the beta part of the bound state wave function. And that is really all following from this expression because 5 minutes? Okay.
For questions.
Okay, I'll wrap up quickly. I'm almost there. So these have a well-defined momentum, so the eigenstates of translation. Translation does not commute with the gauge symmetry. So that implies that these bound states by themselves don't have a well-defined dipole moment. You see like these 2 terms there, the same bound state wave function, but with opposite gauge charges, so with opposite dipole moments. And because of this, you find that the contributions from alpha to alpha scattering just cancel identically. Similarly, beta to beta scattering cancels identically. Only alpha to beta scattering does not vanish because of this relative minus sign. And so you know that if you want to scatter from this to this, the momentum transfer is not just, the momentum transfer you would think, but it's the momentum transfer plus the AFM wave factor. And that's how we get this polarization, which is peaked at capital Q. Okay, and so close to capital Q, so close to the AFM wave factor, you can expand this interaction. And you do actually find a dipole-dipole interaction. You find the typical dipole-dipole form. You can calculate what are these effective dipole moments, how big are they, just to get a sense of how strong is this interaction. But the main point is that it's a dipole-dipole interaction, it's repulsive, and okay, this is the main punchline. After all this work, what do I have? I have a repulsive interaction peaked at the AFM wave vector, and we all know that's exactly what you need to get D-wave superconductivity. And so indeed, if you do the self-consistent, you solve the self-consistent BCS equation, out comes indeed the dx squared minus y squared gap. Okay, so you would have laughed me out of the room if I said you that we found P wave. So it's not surprising we find D wave, but I think it's pretty neat that you can get it starting from these small Fermi pockets. And not just by exchanging usual paramagnons, but actually you have to go through the bound states and then use the projective symmetry, the structure of the bound states. And it's pretty neat that in the end, it all falls into place. And you get this, this D-wave symmetry from a dipolar, an emergent dipolar interaction. One more thing, the work was actually done by Mina and by Arthur. They are two PhD students in Ghent. Okay, well, thank you.
Questions?
Yeah.
Putting ahead of devil's advocate for a second. If I start, you correctly said that you're working in a different situation from large Fermi surface, etc. But if I start with the ordered antiferromagnet, and within this ordered antiferromagnet, I calculate pairing interaction, I still get small pockets, of course. And again,
how do you get small pockets?
Oh,
you're in the order. Oh, you're in the orders. Yeah, sure. Okay, yeah.
Small electron doping in ordered antiferromagnet. And then I do get attractive D-wave pairing interaction, right?
Mm-hmm.
So is there any qualitative difference?
In terms of TC or what?
No, in terms of physics. I mean, the small pockets, attractive.
Yeah, because in that limit, we always start from just microscopic fermions pairing. So if I here would put the charge and the spin on smack on top of each other, I would not have this interaction. This interaction would be killed. I need some. So there's this balance between the interaction has to be not too strong to not put the particles on top of each other, because then I kill this effective dipole interaction. I mean, there needs to be some non-zero effective dipole moment. But then it should also not be too weak, because that same interaction scale also sets the scale of the dipolar interaction itself, because it's some combination of the Coulomb interaction I get. So yeah, I think this is okay, fundamentally a different way of getting, I think. Maybe I'm wrong, I'm not sure.
Yeah, I'm just curious, in your D-wave pairing, there looks like there's like a sign change very close to the center of the bronze zone.
Yeah, good catch. There's a reason for that. Yeah, this is actually not physical, I think. This is because there's actually this band crossing here, and we took the lowest energy state, but I think we should actually there's some crossing here, and I think that's why we get it. I don't think it's physical, yeah.
So what are the spins actually doing? They're in some sort of thermal or liquid state?
You mean just at the half-filled state, you mean?
Well, you're doping the half-filled state.
Yeah.
That you said you want to be in a situation where they're not ordered anymore.
So, okay. The answer that they would form a U1 spin liquid, which is not stable. But then, okay, this is a standard story. Then we hope that with the fermions there, you can actually get this.
But it doesn't really enter in your story.
Well, I mean, again, no, it does. I completely ignored non-perturbative effects for A. If monopoles are everywhere and this completely changes my photon propagator, then yeah, of course, the starting point of my analysis is completely different. Yeah.
I didn't catch it. Did you say what happens in Q goes to zero limit?
For what? What happens? What?
Like in terms of superconductivity, what happens?
Sorry, what Q go to?
Like momentum, a finite Q.
Of what? The Q of what?
In your next slide, you have a. Okay, sorry, we can talk later.
Oh, sure.
More questions? Oh, if not, let's thank Nico one more time. All right, so next speaker is Maine. Christos, sorry.
Okay, yeah, so thank you to the organizers for the opportunity to speak today. So my talk will also be on a different material than we've heard about so far, which is the Cuprates. So these materials have been around for a long time, and superconductivity in them is probably one of the most studied phases we have. There's been this huge outpouring.
Is your mic on? Sorry, is your mic on?
If you're gonna check if the tapping on it, right?
Tapping on it.
Just. That's all.
Okay, yeah, sorry about that. Yeah, so these materials have been studied since before I was born, actually. But just to give some motivation for why I think we're still generating interest today. There's been a lot of unconventional superconductors discovered since, but if you just go by the critical temperature, these are still the best game in town in terms of highest TC. They've really been a playground for exploring all of these unconventional phases over the years. And a lot of ideas about fractionalizations and spin liquids, like what we heard in the previous talk, came from this sort of field. So with that motivation for why we keep studying these, this is the phase diagram of the Cuprates. So on the x-axis is hole doping, and on the y-axis is temperature. And the green blob at the bottom is the D-wave superconductor. And the special thing about the superconductor, or one of the special things, is its normal state. So it emerges from the pseudo-gap state, which is characterized by in photo emission. If you look at the Fermi surface, rather than seeing full Fermi surfaces, you see these arcs. And then superconductivity and all these other competing phases at low temperature emerge from this sort of phase. And you can compare this to what you'd measure in the overdoped side. And what you'll see in this case is the full Fermi surface you would expect from a typical Fermi liquid. So this is telling us that there's something qualitatively different about the normal state that this phase is coming from. There's also other evidence that something unusual is happening. So if you look at measurements of the Hall density, there's a drop in the carrier density as you dope closer to charge neutrality, where the associated value is going from 1 plus P to P. And more recently, actually just in the last year or so, there's been data that came out which measured the Yamaji effect in these materials. So they're able to extract from magnetoresistance some value for the percentage of the Brillouin zone that the Fermi surface takes up. And the value they measure is 1.3%. So this is obviously very different than you'd expect if you had a full Fermi surface. And so this tells us that what we're seeing is some violation of Blenger's theorem. And Blenger's theorem tells us that if we haven't broken any symmetries of our system and we still have translational invariance, then the Fermi surface should be proportional to this 1 plus P number. And this is not what's happening. However, there's a way out. So there's this idea of a fractionalized Fermi liquid, which we heard in the previous talk, where the idea is that you have additional invisible fractionalized degrees of freedom, which are contributing to this number, which you aren't seeing in this counting argument that Oshikawa did when he did this type of flux threading argument. And in particular, if you add an additional spin-a-half moment for every unit cell, this will contribute another +1 to the filling. And so you end up with 1 plus 1 plus P, which is P mod 2. So the idea is that this is how you can get this type of state with a small Fermi surface, where each pocket will enclose an area of P over E rather than P. So then the question, or the questions I want to talk about for the rest of the talk are, how should we think about superconductivity and charge density waves as instabilities from this normal state? And how is it different than these states as instabilities in a conventional Fermi liquid? And what are the implications of this FL4 normal state on something that you can measure in experiment? So we know that it's very hard to measure fractionalization in general, but there's some predictions we can make on the states we find at low temperatures, given that they come from this type of parent state. There's also this puzzle that if the Fermi surface is this small pocket, why isn't this seen in ARPES where they don't really see anything going back around? It just looks like an arc. And so typically, when people have studied FL stars in the past, they rely on these parton constructions. So going back to the days of Wen and Lee, typically you take the electron and then you can write it in terms of a bosonic degree of freedom and a fermionic degree of freedom. However, doing it this way, it can be kind of hard to see how you can go back from this description to observables. So for example, if you use this version of the electron, then you end up with a doping that's proportional to the condensate of the boson, and it's no longer a parameter that you can tune freely. So it's difficult in that sense. So the kind of structure that we'll use to study these parton theories will be the Ancilla model, and this will allow us to capture all these phase transitions. So the Ancilla model was introduced by Yves and Subir going back, I guess, 6 years ago now. And the idea is you take your square lattice of electrons, which is just the square lattice of the Cuprates, and then on each site you couple each electron condo coupled to this other layer of spins. And then there's a second layer of spins which are antiferromagnetically coupled to the first layer. And the idea is that you can obtain some variational ground state wave function for your original electrons by guessing some mean field ensembles for these two layers of spins, and then projecting them back into a wrong singlet state, which will give you wave function on your electrons. There's also some motivation for how you can get some model like this from something microscopic. So if you just take the single band Hubbard model and then decouple the interactions with this spin 1 paramagnon field, you can think about these degrees of freedom as representing the lowest L equals 0 and L equals 1 states of the paramagnon. So there's a connection to this to the Hubbard model as well. So how do we see the Fermi liquid phase first with this large Fermi surface in this model? So for the Fermi liquid phase, what you do is you project S1 and S2 into a rung singlet state such that the C electrons are completely decoupled. So having decoupled the interactions, these are just free electrons now, and you'll measure a large Fermi surface in this case with the usual Luttinger volume 1 plus P. For FL star, what you do is you introduce two sets of fermionic spin-ons for each layer of spins. And then the idea is that each of these are filling one, so each of these has their own associated gauge field, which is enforcing this filling constraint. And then when we take the limit where the condo coupling JK is large relative to J per, this is when energetically you'll condense the boson, which comes from the mean field decoupling of that condo coupling. And when this happens, effectively you have kind of the opposite situation from the Fermi liquid, where you have the first two layers coupled now, and the second layer is completely decoupled from the charge degrees of freedom. And the idea is that now in this last layer, this is where your fractionalized excitations will live. And now if we do the counting in this phase, we see that we have filling 1 plus P in the original electrons, and then we have +1 for the second layer of spin-on. So this will give us our small hole pockets. Each of these pockets will have density P over 8. And if you do some fitting of parameters of your model to Cuprate data, you can reproduce something that looks almost like an arc where you have most of the weight is shifted onto the front side of the pocket, but you can still see the back side going around. And yeah, so this is one way to get something consistent with all this data, including these recent Yamaji measurements. But an important question that we haven't addressed yet is how do these spins fractionalize? So it seems that they're decoupled, at least in the pseudogap phase. We could just put any type of topological order, gapless spin liquid, and everything I've said so far would go through. But we do choose a particular type of fractionalization to study, which is that of the pi flux spin liquid. So this is an SU2 gauge theory where we write the spin-ons in a Sandbu basis, and essentially we're gauging the SU2 symmetry, which is acting in the Sandbu basis. And this gives us this theory where these phases are just fixed such that every time the spin-ons move around a plaquette, you pick up this phase of pi flux. So this is a gapless Dirac spin liquid. You can see there's two Dirac points in the Brillouin zone. And the idea is that even if you end up, or even if you start at charge neutrality in some gapped state, you'll still have some gapless states from this sector. So then going back to the Ancilla construction, we have our renormalized electrons. So we can think about now the F1 spin-ons, and C is just one object, which is coupled to the external or carries the UN electric charge, and then we have our high flux spin liquid in this second layer. And now we want to study the phase transitions from this normal state down into ordered phases as the temperatures decrease. So in particular, we want to study the phase transition from this normal state to superconductivity and charge order. And this will be driven by the Higgs condensation of a boson. So if we take the antiferromagnetic interaction and we do some mean field decoupling on it, you'll get terms like this, where the electron is coupled to the second layer of spin-ons via boson, which is our charge-on. So this is also this boson is also fundamental of SU2. And it also must carry the same flux as the spin liquids, or rather the same SU2 gauge field as the spin liquids. So it carries the U1 EM charge, but it also is charged under the SU2 gauge theory or gauge symmetry rather, because the electron needs to be a gauge invariant object at the end of this. And now the idea is that if we condense these various components of B in different ways, this will give us different types of order. So seeing how this goes, so in the low energy limit, we can think about the bosons will want to condense at the band minimum of the pi flux spin liquid. And you can basically just linearize and then look at the different gauge invariant combinations of condensing bilinears of B. And these are the different types of order you can get. So you get different stripe states, and you also get D-wave superconductivity. There's a time reversal breaking state, which is less important because it's not seen in experiment for these purposes. But the idea is that this particular spin liquid theory naturally gives us both superconductivity and charge order as low energy instabilities. And one kind of suggestive thing that tells us that this theory might be describing some of the phenomenology is if you look at the vortices in the superconducting phase, you can see in the vortex cores the appearance of period 4 CDW order. So this is maybe suggesting some type of intertwinement between the phases, which can be captured by this theory where they're kind of on equal footing. So then the question is, what are the properties of the superconductor? And is there anything observable or any effect that we have to worry about of these additional fractionalized degrees of freedom we introduce? So in the superconductor in the Cuprates, it's known that there's only one node in each corner of the Brillouin zone, so there should be 4 nodes total. This is what happens if you just take a D-wave pairing and put it on top of a conventional large Fermi surface. But when you have these small hole pockets, your naive expectation might be if I just put a D-wave pairing on top of this, I should have 2 nodes in each corner of the Brillouin zone, because I'm also cutting past the backside of this pocket. But this is not what's seen. So this is where it becomes important to take into account that you have these extra degrees of freedom, which are invisible to charge in your parent state. So we actually have one more Dirac cone coming from the spin liquid. And the idea is that when we condense the superconducting order parameter, or rather condense B such that this order parameter becomes non-zero, this will hybridize the Dirac spin liquid Dirac cone with the electronic bands, and these 2 nodes generally will be unstable, and it will leave us with the single node that we expect from experiment. So if you didn't take this sort of install approach, it wouldn't be clear that you would be able to reproduce as part of the experiment. And it's important to take into account these degrees of freedom that you can't see in the normal state. Okay, so there's also charge order, which is observed. So these are period 4 stripe states in general. So there's different periods which have been seen. But I think the most common is period 4. And these have also been seen in various numerical studies of the Hubbard model. And so this is something else that we'd like a theory to be able to reproduce. And we find that if we tune our parameters enough that we can find all different kinds of stripe states with various different periods, and all of them close or competitive in energy to superconductivity. This is all mean field theory, but this is like a good starting guess of the types of phases that you can find. And so then we wanted to reproduce some of the observations which were seen in quantum oscillation data. So It's been measured that when you apply a large magnetic field to measure the Fermi surface, we measure some small pocket, and we know from the Hall density measurements, or rather the Hall resistivity, that this pocket is electron-like rather than hole-like. So it's not actually measuring the pockets of the pseudogap phase. It's measuring some phase which comes up when you input this magnetic field on the material. And so this was accounted for previously by this theory where you just take some large Fermi surface, and then you fold your Brillouin zone such that you have some type of 4x4 CDW, and then you have these electronic pockets which emerge naturally and they have the right volume. So this is a nice story, but it doesn't apply if you don't have this large Fermi surface. And we wanted to see if the same thing will happen if you use this FL star state to begin with. So now the idea is that you take these small hole pockets and you do the same tiling of the Brillouin zone. And again, if you neglect these extra fractionalized degrees of freedom, then the naive expectation is what you'd end up with is you end up with the same electronic pocket you have in the normal Fermi liquid case, but you also end up with this other hole pocket, which has a volume that you would see it in Kwan oscillations if it was there. And so this is not there, and basically this picture wouldn't match the data. But then you need to take into account that this transition, because this is a Higgs transition when you're condensing B, you have these additional degrees of freedom which come into play, again, from the Dirac cones, and these will gap out this extra pocket, and it will leave you essentially with something that can match the original data. Okay, so that's everything, or most of what I had to say about the ordered phases. If anyone has a question, or
Yeah, actually, to what extent is the biflux spin liquid unique in giving you all these things?
Yeah, I mean, like, so you could have taken the staggered flux, like the U1 spin liquid, and that would have given you D-wave superconductivity as an instability, but it wouldn't have given you the CDT phase. So essentially the motivation is that it can give you the right phases at low temperature. Different spin liquids will have different instabilities.
So far, this is the only spin liquid that you found that does all these things.
Yeah, it's basically because the gauge group is bigger, right? So it gets all the phases you have for the U1 case, and you need some type of SU2 Higgsing it down to some field to start with the fermionic spin-on. So this is kind of the most general option, and it gives you 2 of the phases. So coming back to this puzzle, that it doesn't seem in experiments that there's a backside which is observed to these Fermi arcs. So again, if we look at what we would see in our PETs, we see no backside pocket, versus if you do this Ansel approach, you should see some spectral weight on the other side. And we want to see how can this be consistent with this Imagi effect data. So can you still measure some quantized Fermi surface even when you don't measure any spectral weight on the backside of this pocket? And the idea now is that we want to add thermal fluctuations for theory and see if we can reproduce both of these aspects. So the setup now is we're going to use classical Monte Carlo to study this theory. So in general, it would be nice to be able to do something more precise with the full interacting theory. But this is a theory of 2 complex bosons and then 2 fermions and then this gauge field, and it's just very difficult to simulate numerically. And it has a sign problem and all these other issues. But if we only care about thermal fluctuations, then we can just constrain ourselves to look at the bosonic theory. So this is now a theory of classical bosons coupled to this SE2 gauge field. And the idea is that this should be sufficient to capture like finite temperature phase transitions and things like this. So you can imagine that you obtain this type of free energy in the charge-ons from integrating out the fermions, which appear in the full theory with the electrons and high flux spin-ons. So now we tune to a parameter regime where we expect that the D-wave superconductor will be relatively competitive with these different charge-ordered states. So the reason for that will be clear in the next slide, hopefully. And we see that as we lower the temperature, if we look at the phase of the superconducting order parameter and also the relative phase of the X and Y bond components of it, this is clearly going to a D-wave pairing at some temperature. And if we look below this critical temperature where the order is condensing, we can look at a single snapshot of the D-wave superconducting state. And so here what's being plotted is the bond order parameter, the bond density order parameter. So this is not the superconducting order parameter. But if we look at the phase of the superconductor, now we see these vortices. And these vortices are associated with some kind of ordering in this bond order parameter, such that if we zoom in on one of the vortices, what we see in the density is they have these modulations. And if you zoom in enough, you can see that these modulations are actually period 4. So this is something that is consistent with this observation that if you measure the vortices in the superconducting phase, that you should see some type of CDW in the cores of these vortices. And yeah, that's one nice aspect that this can reproduce now that we've seen. And now the idea is that for this phase transition, the proliferation of these vortices should drive some BKT transition. So the way we study this is that in the free energy, we take just the quadratic term, and then we couple it to this additional U1 gauge field, and then we compute the helicity modulus. And the helicity modulus should increase when we go into the superconducting phase, and we see that it does at some temperature. And if we compare the temperature where this happens to this Nelson-Kotzerlitz criteria, so there's this relation between where this critical temperature should be and basically this constant, we see that it falls right along this line. So this is indeed a BKT transition. So one point is that you might have expected, because you're condensing the charge on which alone is a charge 1e object, that you might end up with something different than a BKT transition. But the important part is because your vortices still end up being H over 2c vortices, you get conventional BCS type of transition or BKT type of transition. Okay, and then finally, I want to come back to this normal state above TC, which is the whole pocket, and then see, can we reproduce these arcs with the thermal fluctuations? So now, looking at the same classical Monte Carlo above the KT transition temperature, this is what we see. And so we see that indeed the weight on the backside of these pockets gets suppressed by thermal fluctuations. And now the question is, so in the same temperature regime where this happens, will we still measure some type of quantized Fermi surface, for example, in quantum oscillations? So to do this, we can't do this with the full interacting theory because you need a very large system size to study this. So we go back to the Gaussian theory, and then we just do Gaussian sampling. And this lets us compute the density of states as a function of field. And you see these oscillations from which you can extract the area of the pockets. And the idea is that kind of in this regime, which is being plotted here, this is the regime which is accessible in experiments. And if we look at the various Fermi surfaces in this sort of regime, essentially that corresponds roughly to this one. And we see that even though the oscillations are being damped, you can still see some suppression of the backside, but maybe not as good as you'd like to say that it matches what's been seen in the experiment. And yeah, so that's roughly the scale, the oscillations. So to summarize, the oscilloformalism lets us capture the FLSR theory in a way that accounts for both of these low temperature instabilities from the pseudogap parent state. And we can reproduce these observations in both the charge ordered state and also the D-wave superconductor. And we see a BKT transition in classical Monte Carlo. And something that we still want to resolve in the future is this issue of seeing arcs versus pockets. So we think maybe if there's some quantum fluctuations of the gauge field, this could lead to further suppression and somehow preserve the area measured in quantum oscillations. So that's everything I had to say. So again, the classical Monte Carlo was done with Harshit Pandey, who's a student at IMSC Chennai, working under Sayantan Sharma. Lena and Pietro both worked on several parts of these projects together. And then Matthias, Yahweh, and Jushi, all professors who worked on this. And then, of course, my PhD advisor, Sudhir. So yeah, that's everything. And any questions?
Questions?
So just to kind of learn a little bit. So the idea is the pseudo gap is this pi flag state plus these small pockets of leftover electrons, right?
Mhm.
But then, what is the pseudo gap temperature? A spin liquid should not have any phase transition or any. What happens at the pseudo gap temperature to the spin liquid?
Yeah. I mean, it's not something we've calculated. I guess I can't think of an energy scale that would come in, but yeah, maybe if you computed this in the full theory with the electrons as well, and these additional like parameters, the hoppings, et cetera, there would be some energy scale that would tell you where this would happen. But it's obviously we didn't study that.
More questions? No? Well, if you want to sell your 10 minutes extra training of the next series, we can.
Yeah, kind of just but the low temperature states, once you break symmetry, starting from the spin liquid, is the counting of the pockets. So are any of the low temperature states actually spin liquids, or would the broken symmetry states
No.
have enough broken symmetry to count this P/8 size of the pockets?
So the low temperature states, you're Higgsing the SU2 gauge field of the spin liquid when you condense P, and that's what gives you the ordered states. So like you could think about having like an SC star phase or a CDW star phase.
Exactly.
That's different.
Are they stars or are they normal?
Normal.
They're all normal.
Yeah. So the parent state is fractionalized, the low energy states aren't.
So it's obviously non-trivial to introduce all the experimental facts, but you also mentioned like there's one prediction. Could you maybe repeat what that was, or are there other predictions coming from this theory?
Yeah, so I can comment on actually the electron build side. So if you look at the ARPES data in the superconductor there, it seems like you have something that looks like a node appearing at pi/2, pi/2. But like you say, like the normal state in that region is gapped, so you shouldn't see any spectral weight there. And this is something that we predict that the node will emerge basically as soon as you condense the order parameter, because you have this additional Dirac cone, which is there. So that will appear when you condense B in this theory, but you don't need to start with any spectral weight in the normal state. So that's like a prediction that we're hoping maybe something like that can be seen and studied more.
Yes. So is this P/8 the Imagi effect like really a fingerprint of a full star, or can you get it from like can you also get it from like an antiferromagnetic pocket?
I guess so. I think antiferromagnetic pocket would give you P/4, or yeah. So I don't think so. And on top of that, there's not supposed to be any long range order, at least at large enough temperatures. Yeah.
The other questions? No, let's take big overtime. Our next speaker is Pavel Nosov.
All right. Can you hear me?
Yes.
Very good. Okay, so first of all, I would like to thank the organizers for putting together this wonderful workshop. I'm enjoying it a lot. So today I would like to tell you about some story about what sort of new and interesting physics could emerge in composite Fermi liquids if we add just one simple new ingredient, which is the broken inversion symmetry. And as you will see, this story has some relevance to the recent and ongoing experiments in germ bands of twisted MOT2 and rhombohedral graphene. So this work is done in collaboration with Darius Shi, whom many of you know very well, and who's currently a postdoc at Stanford. And you could find some details of our work in this recent archive paper, and there's going to be another one soon on archive as well. All right, so let me start with some general introduction. So luckily, due to all the wonderful talks this morning, and especially due to a very nice talk by Adi this morning, I don't have to go very deep into the discussion of the fractional quantum Hall effect. Of course, we all know and understand this picture. But nevertheless, just to be on the same page, let me remind you some basic facts focusing on composite Fermi liquids specifically and half-filled Landau level story. So here is the plot that we all know and love. That's the resistivity, longitudinal and pole resistivity as a function of the magnetic field, and then two-dimensional electron gas as a function of the magnetic field or the filling fraction. And of course, we have all these beautiful quantized fractional quantum Hall plateaus where rho xx is 0, rho xy is quantized. But also, if you look closely at certain parts of this figure, you will see that there are these interesting states that occur at even denominators, at fillings with even denominators, where instead of having the quantized Hall plateau with 0 rho xx, what we see is some kind of interesting metal where rho xx is finite and non-universal, and rho xy is not quantized, and it varies roughly linearly with the deviation of the filling. So the appearance of this kind of metallic compressible state in a strong magnetic field is very surprising, because from the single particle picture, we don't really expect metallic behavior. We have Landau levels, we have cyclotron orbits, and so on. So seeing this metallic state is very interesting and exotic. And of course, this is all understood, well understood in the past. Traditionally, so we want to think about this metallic state, let's say in context of the Landau level, in terms of the composite Fermion framework, which again was very nicely summarized this morning by Adi. So here I'm just providing some basics. So we start with a two-dimensional electron gas and a magnetic field. Let's say we have 2 flux quanta per electron. And then from the theory viewpoint, of course, this is a very problematic starting point because we have massive degeneracy at Landau levels, and fractions are very important, and we do some non-perturbative effects because we lift this massive degeneracy. And we would like to have some kind of change of variables where we could go to a different vantage point, which would provide us with a nice description, at least at some mean field level, and then we could incorporate corrections. So this change of variables is known by the name of the flux diffraction transformation, which is when we formally define these composite fermions as bound states of electrons and the number of flux quanta, in this particular case, 2 flux quanta. And then this transformation is very useful because we can do simple approximations. For instance, you can smear these flux cubes attached to electrons to composite fermions, and then composite fermions will feel 0 net effective magnetic field, which will be this star. And then we basically end up with a mean field state where we have these composite fermions that do not experience any magnetic field. And we know what these fermions are supposed to be doing. If any fermions at finite density and no field, they will form a Fermi surface. And that's what accounts for most of the experimentally observed phenomenology in the half-filled Landau. So this state is kind of a metallic state of composite fermions, and was originally understood in the seminal work by Halpern, Lee, and Reed. So it's known as the HLR theory. And of course, many other people contributed to these ideas in the early days, and there was a lot of follow-up work clarifying various interesting aspects of this. Of course, I also want to emphasize that this is not a simple kind of trivial metal. It's a very strongly correlated metal. And in particular, these composite fermions are strongly interacting with emergent gauge field fluctuations, which we introduced along the way in other. So what I would like to stress is the composite fermi liquid theory is really a story of success, because a lot of its predictions were actually confirmed experimentally with very good accuracy and kind of striking that such a successful theory could be developed for this strongly interacting, strongly correlated state. So in addition to what Addie mentioned this morning, I would like to maybe stress a few other examples of the experimental signatures of the composite Fermi liquid, which have to do more closely with the Fermi surface structure. So it's these are experiments that are really probing the Fermi surface of composite fermions. So one aspect has to do with the deviations from exactly this hot-filled point where you go a little bit away, in which case the composite fermions experience some small residual magnetic field B star. And of course, as we would normally expect for metals, there should be some quantum oscillations. In this case, should make up the Haas oscillations of the longitudinal resistance, which are periodic as 1 over B star, and the frequency is set by the Fermi volume associated with the density as expected from the C. There are also different commensurability oscillation experiments where people try to add, let's say, various periodic structures, periodic scalar potentials, either this form or some dots, and then a composite fermions of cyclotron orbits, then one should naturally expect commensurability, resonances, and resistance as the radius of the orbit is varied with respect to the periodicity of modulation. So all of these are observed and actually match quite closely to their predictions. Of course, there are other interesting aspects. For instance, the confirmation. One of the sort of indirect confirmations that we have this composite Fermi liquid state filling is that we also observe all the neighboring gene fractions, which could be viewed as daughter states of the CFL, as the effective field is becoming stronger and stronger. And there are also confirmations coming from finite Q transport, which will be quite important for what I will tell you next. Finite Q transport associated, for instance, with surface acoustic wave experiments, where really was being probed this sigma XX longitudinal conductivity of finite Q. And in a CFL, the prediction is that it should grow linearly at small q, whereas in a normal Fermi liquid, the prediction is quite opposite. You should get 1 over q or things of that nature. And this has been measured, so this is really a smoking gun signature of the CFL. And there is, of course, lots of numerical evidence. For instance, I would like to highlight this recent work that uses some numerical techniques in order to calculate specific heat of this fluid state. And the prediction from the HLR theory is that this specific heat should scale as a fractional power of temperature, low temperature, if the Coulomb repulsion is sweet. And this is what was seen in this. So this is sort of the confirmation that this is a strongly correlated metallic state, sort of non-permanent. All right, so with that being said, so we'd like to move forward to the present day, and now the story about composite fermions and composite fermions specifically is sort of becoming central again in our community due to the recent discovery of the fraction anomalous quantum Hall effect. So now we can have all the same stories, but in the absence of the external magnetic field, and originally it was observed from Q-state and Q2 in the Long's group. And then it was observed from rhombohedral graphene and juice. Here I'm just showing this plot from the rhombohedral graphene, which we saw in the previous talks. And here I would like to just focus on the situation at half filling. So of course there are all these very interesting and nice fractional states that are observed, but for what I would like to think about the half filling state as the goals. So the experimental evidence for the existence of this kind of anomalous composite Fermi liquid in this context is a little bit, it's not as detailed as what is known for the Landau levels. So in particular, what is observed is the hierarchy of these field for the longitudinal and Hall resistivity. In particular, longitudinal resistivity is finite and much more than rho xy, which is not quantized, and it varies roughly linearly with the filling fraction with filling. There's also some evidence in Q-state 1, 2 coming from trine photoluminescence. For instance, we could take advantage of the fact that these systems are semiconductors, and there's some nice trine spectroscopy techniques that one could apply in order to sort of probe the single electron spectral function, which is supposed to have a pseudo-gap behavior in the half-filled state because electrons are not really low energy excitations anymore. It's composite fermions that are really low energy particles, but they're kind of orthogonal to electrons, so we should see pseudo-gap features. So some of the indications of this were observed in this nature. And of course, there's some very nice and numerical work that shows that this anomalous composite Fermi liquid could arise in realistic models, for instance, of twisted MIT2. So there were some nice results by the Harvard and MIT groups where they did the MRG and EB, and indeed they find that there's some evidence for the existence of this anomalous composite. All right, so with all that being said, of course, we would like to ask the question, is there anything new and interesting that we could learn from the setting of the fractional anomalous quantum pole effect with respect to composite fermion theory? Is there any way how we should interrogate composite fermions, which was not previously possible in line alone? Maybe we could learn something interesting. So, of course, there are many important aspects of the situation without magnetic field. Now, some of the basics that come to mind are that there's a very strong influence of the underlying lattice potential. There's no Galilean invariance. And the band structure is kind of more easily tunable by the application of the external displacement field. So we have a lot of tunability in these systems. And the existence of the lattice, and in particular breaking of the Galilean invariance, is kind of very, very important, at least for what I'm going to discuss. And I'm taking a very simplistic approach, and I'm just looking at the experiment, and I see that the real symmetry of the problem is not fully rotationally invariant, but it's actually broken down to C3 due to trigonal warping. That's just fact coming from this experiment. These systems, both twisted MOT2 and Robichito-Graphene, have trigonal warping. So the proper symmetry that we should be thinking about is really C3, which doesn't have inversion. So that simple ingredient we would like to kind of incorporate into the old stories about composite Fermi liquids. So we'd like to say that the presence of this trigonal warping and the absence of the inversion symmetry, should be manifested in some way in the low energy description in terms of composite fermions. Particularly, we would like to think that the Fermi surface for composite fermions, the top filling of these Fermi bands, should have some degree of trigonal warping, so it should look like something of this form. It should be symmetric. So that's the kind of starting point that we assume. We of course don't have any microscopic sort of reasoning here, but we would like to just argue by symmetry that the underlying lattice is C3 symmetry and the composite fermion surface will also be C3 symmetry, at least to some extent. And then we could ask questions: does this breaking of inversion symmetry teach us anything new about composite fermions? And the answer that I would like to give is that there's actually surprisingly a lot that we could learn, a lot of new interesting physics. And in particular, I would like to focus on two specific results that we found. First one has to do with transport signatures of this composite Fermi liquid with broken inversion symmetry, and in particular, the manifestation of the non-Fermi liquid aspect of the CFL that could be probed in transport, which is not really possible in the context of Landau levels. And the second point will be about some new interesting gapless and topological paired state of composite fermions that we could get with broken inversion, which we call composite Bogoliubov Fermi liquid. Why I call it Bogoliubov Fermi liquid. Right, so this is the motivation, and these are the 2 points that I would like to discuss. All right, so let me start with the story about transport. So first of all, just in the Landau level context, let me just briefly remind you, and again, this is kind of related to what Adi just talking about this morning, but in a little bit more detail. So if we start with the Half-field Landau level, and we have Coulomb repulsion that is free, that it's known that the composite Fermi liquid is actually a non-Fermi liquid, meaning that the quasi-particle excitations on top of the Fermi surface are short-lived. They have very strong scattering rates that scale as energy to some fractional power, in this particular case, 2/3. And the scattering rate becomes parametrically stronger than the energy of the quasi-particle itself. So the quasi-particles are strongly interacting even asymptotically close to the Fermi surface. That's in striking contrast with the Fermi liquid theory, where the quasi-particles are becoming more and more well-defined closer you get to the Fermi surface. And in addition to that, the gauge field fluctuations are very much alive, and they're Landau overdamped due to the coupling to the Fermi surfaces, to the Fermi surface, and they acquire some Landau damping and the non-trivial dynamically strong. So this Z here is defined such that Z equals 2 corresponds to the upstream Coulomb case, and Z equals 3 corresponds to the stream case. So then we would like to ask, okay, so there's this aspect of the composite Fermi liquid, which is the long-term liquidness of the quasi-particles. Can this actually be detected? So none of the previous experiments that I showed you, at least to my knowledge, this aspect of the story was ever observed. We know it should be there from the theory. In numerics, we also see this, as I said, this t to the 2/3 scaling of the specific key. It's actually, it's related to this power 2/3 here. So, but in experiment, of course, we haven't seen this yet. So is it possible to detect it from that? So the short answer to this in the context of the Landau level is no, because we have very strong constraints, for instance, on how the optical conductivity is supposed to behave in the presence of the magnetic field. We have the statement known as the Kwan theorem, which is a non-perturbative argument that works for arbitrary interactions in the Landau level. And we know that the conductivity just has to be of this form. It just has two delta functions centered at cyclotron frequencies, and the prefactor is completely universal. And there's the conductivity in this sense is completely doesn't know anything about this very interesting dynamics of the Fermi quasi-particles that is hidden in the property. So of course one could say, well, Gaussian invariance could be broken. We could sort of go away and try to introduce dispersion for composite fermions that's not of the p²/2n form, and that will kind of remove this exact constraint. But nevertheless, it turns out that there's still very strong constellations if you try to calculate the corrections to transport coming from the H fluctuating. In particular, these constellations generically occur for any convex Fermi surface with inversion symmetry. So this aspect is not kind of emphasized before in the literature, but that's kind of the implicit assumption among these prior works. So for convex Fermi surfaces with inversion symmetry, if you try to calculate the effect of these singular behaviors of composite fermions, you find that the longitudinal resistance as a function of omega might have some fractional power of omega here, but the coefficient of that turns out to be exactly the same. And this was clarified by these nice works, and a lot of people who contributed to this are in the room. The reason for this is actually purely kinematic. It has nothing to do with the Stroll coupling. It has nothing to do with the gauge. Well, it has nothing to do with non-Fermi liquidness necessarily. It's just a consequence of the fact that the gauge field propagator contributes strongly to transport only at small transport momenta. Just you could see that the pole is sitting in a small cube. So if the non-Fermi liquid physics shows up, it should appear from small cube transfer. And if we have a Fermi surface that is convex and it has inversion symmetry, then basically the only scattering channel that you could imagine is the one where you have fermions at momenta k and minus k on the opposite sides of the Fermi surface, and then you try to move them sort of together in opposite directions such that they remain on shell on the Fermi surface. But it's easy to see that this process doesn't really relax current. So even though you do have these processes, they're not contributing to the conductivity in any significant way because there's no current relaxation, so that you end up with, again, no correction of the singular type. So there might be some sub-meaning corrections, but those are not featuring the universal scale behavior of the so this was understood, and now we would like to revisit this statement in the context of this CFL with broke down. And so here's just a technical slide where I would like to explain the starting point. This is a standard HLR Lagrangian, where we have the first term here is just the Fermi surface of composite fermions coupled to the H field. And the only new ingredient compared to HLR is that this dispersion here knows about the symmetry. Then there's Coulomb repulsion, it could be screened or unscreened. And then there's the Chern-Simons gauge field that is coupled to the fermions here. And this Chern-Simons gauge field implements the flux attachment, and that's what makes the story interesting. So now we can go for the actual calculations. Okay, I don't want to get into the details, so I could take this theory, calculate the standard corrections to the current correlator. Some of these are the important ones are shown here, and there's +7 more. You know, you could, if you're serious, you could try to do it. Yeah, so we did this, and the outcome is very simple. Outcome is that if you look at the finite frequency behavior of rho XX, there is indeed a fractional power that you get, omega to the power 4 over z, where z is this dynamical exponent that I introduced earlier. Z equals 3 is the case of discrete Coulomb repulsion, and z equals 2 when you have unscreened.
And it's either OXX or sigma XX equivalent. Right?
Well, you need to invert you have to go through the Yorfel-Larkin rules and invert.
Yeah, but since
Yeah.
you're dominated by the hollow resistivity, then sigma XX will also go like omega to the same power. Sigma XX is proportional to XX usually.
No, you need to invert. There's a transimence contribution.
Sigma diverge.
Yeah, sigma would. So if you start with the composite fermion site and you just ask how does sigma XX on the composite fermion site looks like, it would have a divergence. It's small.
Yes, but when you translate it to the electronic sigma XX,
Right.
it would look like this, I believe.
Yeah.
Right?
You need to invert.
Yeah. Okay. Let's look at it.
Yeah, but the question is, there is E square over H in the off diagonal. So when you invert, that's much larger than this.
Yeah.
So the real part.
It's proportional to the conductivity.
Yeah. So yeah, you need to invert properly for the yoke.
So how does this result depend on the strength of trigonal work?
Right. So the free factor here is finite, but of course, if you send the trigonal working to 0, then the free factor is going to vanish. So if you have very weak trigonal warping, then the free factor here would be small, of course. So in order for this to be observable, we need some kind of substantial degree of trigonal warping.
Quick technical question. If it's too long to answer, take it and answer later. You said that you wrote lowest order diagrams.
Mm-hmm.
It's the same as we did. But technically in this situation, since you are doing this as a station when boson is massless, you would assume you expand in self-energy with the lowest order diagrams.
Yeah.
So this result is technically valid only for frequencies larger than some particular one, where omega 2/3 if z is equal to 3 is smaller than omega.
Right. So yeah. So strictly speaking, we're doing kind of a perturbative calculation, right? So these fermion propagators are free fermion propagators. So in that sense, we're not inserting the self energy into the fermion, and this is controlled if you introduce some kind of large n limit, and then this would be strict statement would be that you're calculating a 1/n correction to the optical conductivity. So this is very much in line with all the previous works, but we just wanted to emphasize that even at this level, trigonal warping by itself is enough to give you a finite answer.
I'll follow up a technical question with a technical question. So the expansion that you guys are using, this is HLR-RPA, or are you using Darius's magic cut and glue procedure for?
No, this is nothing fancy. It's just, these are RPA dress propagators, and these are just free fermion.
Did you guys ever use Darius's magic procedure?
So we think we should look at this more carefully. Yeah. So we just wanted to sort of be in the same realm of all the previous works, and just to emphasize that even in that setting, we could get some finite interesting answer. But of course, now once there's no consolation, we could try to think more carefully about doing this, taking this to a new level more proper.
So out of the 12 diagrams, who's the one that gives you the omega to the fractional power?
Yeah, so all of these give you the same scaling with frequency. It's just in the old literature, they all cancel if you add them up, but here they don't. Yeah, and plus 7 are actually the ones that are coming from the diamagnetic vortex. So this is a paramagnetic vortex, and there's also a square. So those turned out to be, we checked carefully, those turned out to be subleading in their scaling with frequency.
So it's those 5.
Yeah. Any other questions? Okay, good. So just a simple explanation, and I sort of alluded to this already, but kind of a simple pictorial explanation for why this is possible. Again, for the inversion symmetric Fermi surface, you basically cannot relax momentum, but you cannot relax current if you try to scatter with small q. But here, with this trigonally warped Fermi surface, you could easily identify some kind of non-generic pairs of q and p prime that are not just opposite to each other, such that you could still sort of scatter on shell, but at the same time, the difference in velocity in such a process would be substantial.
Is it so that the z equals 3 is for the on screen for the on screen?
For the screen case.
Screen case. Yeah.
Yes. Q squared plus omega. Right. And of course, I'd like to highlight that this is kind of similar in spirit to the story about the convex concave transition. So if you have a concave Fermi surface with inversion symmetry, such non-generic scattering channels would also occur. But for us, we don't even need to go this far. Any amount of trigonal warping would be sufficient, even if the Fermi surface is convex. All right, so moving on, there's some interesting stuff about finite Q transports as well. So this was optical conductivity. As finite Q, we also have some interesting results, in particular related to the surface acoustic waves. So the setup there in the usual experiment is that if you have a two-dimensional electron gas, you have the electric on top of it, and then you introduce a propagating surface acoustic wave here, and due to this piezoelectricity of the background, that induces some scalar potential for an underlying electron gas. So then what is measured is the frequency shift and the attenuation rate, and then these quantities could be expressed either with the longitudinal conductivity of the system, or if you use continuity equation, it could be expressed with the density correlated at finite q and frequency that's much smaller than q, because you're probing frequencies of the order of basically velocity of this propagating wave times q. So that's the regime where Landau damping is essentially. And then one interesting aspect of this system, of this present situation with inversion symmetry breaking, is that Landau damping for us actually has both. Okay. It has both real and it has both reactive and dissipative parts. It has both real and imaginary components. Normally, this gamma here would be purely real, so the pole of the gauge propagator would be on the imaginary axis. But here, it's actually shifted away from the imaginary axis, and there's both real and imaginary parts present. So the gauge field has some interesting dynamics of its own. But also, this allows us to actually probe some degree of directional asymmetry in the system if we sort of get information for this frequency shift and the attenuation by looking at anti-symmetric combinations of q and minus q. We could sort of try to identify these imaginary components and get some sort of quantitative estimate of the degree.
Sorry, this gamma depends only on direction of q, or
this gamma here is a
direction.
Yeah, that's right. So there's a more general form of this line.
So presumably then the amount of warping should control the magnitude of imaginary part, correct? So which parameter controls?
Right. So the degree of the warping, yeah, it's going to appear. These gammas will be explicitly small if the warping is small. This gamma imaginary will be small.
Fine.
Right.
Quick puristic question. Imaginary part of gamma contains extra sign omega?
Well, this is already on the real frequency axis.
Yes, exactly.
Yeah.
Is there any additional sign omega?
No, I don't.
Imaginary part is odd. I omega over q is odd piece in omega.
It's probably already
Are you saying
retarded.
that the real part is
It's retarded. It's continued properly.
Yeah. I have to. The pole has to be in the lower half plane. If it's on the Matsubara axis, there is a sign of omega. I agree with you. But after analytically continue, I can show you.
Yeah, sure.
All right. So this is something that we expect could be in principle detected in surface acoustic wave experiments if we prefer to do this for two-dimensional T2 or on the Dipole-Dipole. All right. So any questions about transport? I guess now.
Yes, actually, on the finite cube.
Right.
So what exactly is the signature that you'd like people to look at?
Right. So I could perform the surface acoustic wave experiment, right? I could measure this frequency shift and the attenuation rates at some q, right?
And usually you extract sigma xx linear in q, and here you will extract what?
Well, here I would like to look at these combinations. Let's say I would like to look at the frequency shift at q and minus q, and I would like to subtract the two. So in the inversion symmetric system, this would give me nothing. Here, this would be some kind of non-trivial function that is direction dependent, and I can sort of try to extract a degree of anisotropy from this. All right, so this was the part about normal state transport and some interesting finite Q responses of this CFO with Bultinck inversion. So now I would like to briefly mention some other story related to this system when we try to consider pairing, right? So in the normal CFO context, we know that since we have a Fermi surface, it's very natural to consider PCS instability, which is of course not really weak coupling anymore because the gauge fields are included and so on. But nevertheless, if we try to pair composite fermions, the natural candidate for the pairing order parameter would be the P plus AP order parameter because we don't have spin and the time reversal is broken. So that's the usual story. It's a fully gapped superconductor of composite fermions. And on the electron side, that translates to kind of quantized quantum Hall state, fractional quantum Hall state with non-abelian topological order. That's known as Moreau-Reed state or the Plattian or any of the versions of the Plattian. And there are, of course, the indications of this in experiments. In particular, the quantization of rho xy is observed in the second, first excited Landau level, and rho xx seems to have a dip. And the daughter states that are observed are also different from the usual CP. And there's some evidence from the numerical calculations that similar type of phenomena should be in principle possible in context of the term bands. So now we would like to ask that. So what the breaking of the inversion symmetry could change for pairing, and the simple argument shows that the kind of fully gapped superconductor is not the most generic outcome, and in particular, if you try to drive some kind of quantum phase transition from a CFL state to a fully gapped state, in between, generically, there would be an additional intermediate phase that would be a superconductor of composite fermions, but with gapless Fermi surfaces of Bogolubov quasiparticles. So here I'm just showing some particular kind of simple mean field example where we could imagine that we do a simple mean field story for these composite fermions, where we have some Bogolubov Degen Hamiltonian. The dispersion has some particular orthogonally warped structure, which is shown here with this black line. And then if I try to pair it with the P plus AP order parameter in some mean field fashion, I would generically end up, for not too strong pairing, I would generically end up with these red pockets that would correspond to gapless surfaces for these Bogolubov excitations. And this is just the simplest example. All of this is, of course, generalizable to more interesting and probably more realistic settings where you have PDWs, but let me just stick with this Q equals 0 example for now. So this is very generic with inversion symmetry, at least based on a symmetry perspective. And we would like to argue that this kind of interesting state of paired composite fermions with these gapless Bogolubov excitations is, of course, it's first gapless, but also it's kind of topological, and we call it composite Bogolubov Fermi liquid, referring to these Fermi surfaces. That's the Bogolubov Fermi liquid component of it, and composite is just referring to the fact that we're dealing with composite fermions. Right, so this could be incorporated in the HLR story by standard means, and then here I just would like to summarize some of the main properties of this state, and I would like to contrast it with the metallic CFL and the fully gapped Papian state. And I would like to go through the list of properties, and I'll tell you the differences that we have between all these. So first we can start with longitudinal resistance. So as we discussed in the metallic CFL, it's not quantized. In general, it's greater than 0 if we have desorder or anything else. Then the whole resistance is not perfectly 2h over e squared. On the Papian side, of course, there's perfect quantization, and then we have perfect quantization as well, because this is a superconductor of composite fermions. It has superfluid stiffness and so on. So this could be understood from local arguments. So now if we ask about compressibility, then the metallic state, of course, is compressible. The Papian is fully gapped, so it's not compressible. And this composite Bogolubov Fermi liquid is also incompressible. So this is a little bit harder to understand given the fact that there are these gapless surfaces. But okay, so the kind of theoretical argument is that the compressibility is related to the particular limit of the density correlator. In our case, because the gauge field associated with the flux attachment is actually Higgs, this correlator has the structure, in particular has this Q squared up front. And the finite superfluid stiffness guarantees that the compressibility is right. So in terms of specific heat, the Papian is fully gapped, so there's exponentially small specific heat at low temperatures. The CFL with spin Coulomb would give me T to the 3/3, and then this state would give me T linear specific heat. So that's coming from these gapless neutral Fermi surfaces, and it's T linear and not T to some fractional power again, because the gauge field is Higgs, so there are no non-Fermi liquid corrections associated with that gauge field. So really, we're dealing with a good Fermi liquid, well-defined quasi-particles. Okay, that I'll explain. So there is, of course, consequences for thermal hole conductance. So in the Papian, it's quantized. In both CFL and the CBFL, it's not quantized, again, due to the presence of these neutral gapless quasi-particles. There are no quantum oscillations in this state, and that could be understood from a simple argument that the Bogolubov quasi-particles are actually superpositions of particles and holes, so they don't really have well-defined charge. So if you try to apply Onsager quantization argument and you try to sort of drag this quasi-particle along its pocket, then it changes sign, so there's no semi-classical quantization present. Then there's some consequences for sort of charge fluctuation, for density fluctuations. In particular, if we look at the structure form factor, which is something that people could calculate in exact diagonalization or other numerical techniques for the composite Fermi liquid, there's this non-analytic term that scales as q cubed times logarithm of q, it's small momentum. And in our case, there's also a non-analytic term that goes as q cubed, but without the logarithm. And the absence of the logarithm has to do with the fact that the gauge field is actually fixed. So HLR, this logarithm, has a special meaning. It comes from the overdamped mass dynamics of the gauge field. For us, it's absent, but nevertheless, there's a q cubed term. And for Fathian, of course, this function would be fully analytic at C. And finally, one of the interesting aspects is that if we try to look at the ground state degeneracy of this state, if we, let's say, simulate this problem on the torus, then in a composite Fermi liquid, there's no ground state degeneracy. In Fathian, the ground state degeneracy would be fixed. And for us, actually, the ground state degeneracy is 2. There's still some protected topological ground state degeneracy, even though we have these gapless neutral Fermi surfaces. So I probably don't have time to explain this particular part of the story. It's a little bit more involved, but kind of for the experts, the story is roughly that you could start with a strongly coupled, a strongly paired picture where you have just the one level 8 refinements theory. You could look at its anion content, and you could try to identify which anion in that content corresponds to the Bogoliubov fermion, right? And then that fermion, since it's gapless now, if you have anions that braid non-trivially with that gapless anion, or if they fuse to each other with that anion, then they become ill-defined. So the only anion that is actually stable in that count would be the semyon, and that's what provides this topological ground state degeneracy.
And here you mean that the splitting between these two would be exponential,
Yeah,
and
so
the rest is power law.
That's right. So in a finite size scaling, this splitting would be exponential, and then because I have these other gapless excitations, there'd be some power law splitting for those other side states. All right, so here's my conclusion. So indeed, so broken inversion symmetry, despite the fact that it's such a simple ingredient, it reveals a lot of new interesting physics related to composite fermions. In terms of normal state transport, again, as I emphasized, there's this interesting fractional scaling of the longitudinal resistivity as a function of omega, which is sensitive to the dynamical critical exponent of the problem. And it could be really a probe of non-Fermi liquid physics. If we could measure it in the systems, that would be the first indication of non-Fermi liquid observed in this way. And of course, there's a lot of interesting results related to finite Q responses in particular surface acoustic pairs. And then in terms of pairing, so we propose this new state, which is what we call composite Bogoliubov Fermi liquid. It's an interesting state because it's sort of in between. It shares a lot of features with both CFL and the Fathian, the gap version, and it exhibits a lot of kind of mixed properties. So it has both quantized fractional quantum, it has both quantized Hall response. It has twofold topological ground state degeneracy in force. It's incompressible. It has a fully gapped single electron spectral function, but also it has all these kind of metallic properties. It has T-linear specific heat, unquantized thermal conductance, Landau damping, and non-analyticity in the structure factor. And of course, there's a lot of interesting questions about that in the future. With that, thank you for your.
Masha, can you go to that slide that we discussed for your polarization bubble? Yeah, I think this one. Yeah, I have kind of observation for you to consider. So in addition to all of these quantities that you discussed, there is one more that's been measured and calculated, and I think that this would lead to a new result. So this is from Eddie and Shishkin. They looked at the Coulomb drag and nu1/2 bilayer. So in their case, they also have the same form of the spiral rho, and if there is no gamma, then there is a characteristic Q, which is a cubic root of omega that sets the scaling of a pole in this picture. And so this translates to a fractional temperature dependence of the drag resistance, which is 4/3. In your case, because you have now imaginary part of gamma, that I times that imaginary part would start competing with the long wavelength limit of this composite picture. So it means that there is a characteristic Q where your gamma would win against this guy. And so then the scaling of Q with gamma will give you a new temperature dependence for drag resistance.
I see. Okay, that's very interesting. Yeah, let's discuss more. Yeah. Very good.
Sorry. And Maria, there is Andre, Eddie, Art. That's the order.
Dino.
Very quick question. So here
would it two lines question of would it be the energy scales for the size of the Fermi surface, would they be visible with SAW?
Scales. Well, I mean, I don't have microscopic understanding of. I'm not sure what you mean by scales, right? It's all very experiment specific. I'm just trying to say that on symmetry grounds, this is possible.
But it's also important, like just to see, right? Like, would the energy scales that are like frequency scales that are comparable for SAW would be able to match those?
Yeah, I mean, it was in the context of the Landau level, surface acoustic waves were used to probe exactly the physics that I'm discussing, apart from the inversion symmetry broken stuff, right? So that's new. So I imagine if one could do it in crystalline motility or hydrographene, that would be amazing.
And related, is there a reason why nonlinear optical probes like SAG wouldn't work here?
Like what specific setup?
Like some standard probes to probe like inversion symmetry breaking.
Well, I mean, yeah, if you have some particular probe that is sensitive to inversion symmetry breaking, of course, that should be.
Yeah, it should be. I mean, in principle, it can be like second harmonic generation or some other.
We haven't thought about nonlinear response, yes, but that's of course important to consider. Yeah.
So in this non-inversion symmetric case, so I guess there's no obvious reason why favor Q equals zero pairing compared to finite Q pairing.
Right.
So is there anything interesting about the pair density wave?
Well, I mean, the story, if I, with pair density wave, I'm also going to generically end up with these Babalubov Fermi surfaces, right? So in addition to that, there will be some translation symmetry breaking.
Yeah.
Yeah,
but it can have other possibilities.
Right. So we haven't thought about this very deeply. I think
fractional. If you think about the superconducting side, it can have these fractional.
Right.
Vortices. What do they correspond to in the?
Yeah, that's a good question. So the vortex, all the vortex physics, we're thinking about it. So far, I kind of avoided the question of what happens if I deviate a little bit away from half filling. Let's say what would be the daughter states, what the vortices would do. These are all very interesting questions, and in particular, if there's a PDW there. But yeah, I just would like to stress that all the properties that I listed, those are kind of universally there, irrespective of zero Q or finite Q.
Same question as Aries, but formulated slightly differently. Correct me if I'm wrong, but it sounded like you said, let me choose particular paired state, P plus IP, and then you calculate Fermi surface for this state. This Babalubov Fermi surface.
Well, this is
what if,
for
question. What if you have fermions with self-energy, right. You have polarization bubbles, so you can, polarization, you know effective interaction.
Right.
Can you solve the full dynamical problem also, assuming that pair may have a finite momentum?
Yeah, it becomes very, I mean, it's possible, it becomes very complicated. So in the context of the Hatfield-Landau level, people did very extensive Migdal-Youngberg calculations.
You will have a special situation. You have broken inversion symmetry.
Right. So one would have to repeat that analysis with inversion symmetry breaking, which is, of course, it should be done, right?
So it will take you half a day, no more.
No.
On that note, then we can get your answer tomorrow morning. Sorry, did you?
Yeah.
100, I swear.
So I wonder, can we get this non-Fermi liquid physics just taking a non-invergent symmetric Fermi surface in this rhombohedral graphene or other, and couple it to QED or to phonons? Is there any chance of getting something singular there?
You mean to some critical fluctuations of some quantum critical?
Yeah.
I mean, so the thing is, you could apply the same calculation essentially to any Hertz-Mills theory. So if you assume the Fermi surface for electrons that has this orthogonal warping,
exactly,
then the calculation would go essentially in the same way. So it's just a kinematic constraint that's lifted now. Yes.
But now we have lots of them. So can there be some
QCP in mind, or
no? I mean we have lots of Fermi surfaces which are not circular.
Right. But now you also need a quantum critical point, right? You need quantum critical fluctuations.
Or just coupled to QED to the electromagnetic field. Of course, there you have 1 over c squared all over the place. So
To QED, you mean just
to the electromagnetic field.
but presumably,
Yes.
3D.
yeah, that's.
You want
I mean, you want some
2D,
singular effect coming from some kind of boson, right? That's
So to the electrons to 3D QED would give, I think, singularities of this type.
But isn't it what you are actually
That's
considering?
basically the calculation here because the Chern-Simons doesn't matter.
well, yeah. We like with the unscreened.
Yeah.
Well, but then the effect would be kind of very hard to see, right? So the power here is fractional, but if z is 2, then you would see something completely different. It's 4 over z, right? So z 2, then it's omega squared. Here, I think really maybe the nice thing is that it's a fractional power.
Yeah.
So that could be more easily detected.
So the second question is about the extent to which the Chern-Simons does matter. So about the ground state degeneracy.
Mhm.
So am I right to think that that state has completely decoupled from the bulk semi-on edge modes?
Right. So we need, yeah.
Can I think about those as evolving from, because there already is kind of an edge degree of freedom in the
Just in
CFL
the
that just
CFL,
couples
yeah,
to the
that's-
bulk.
I think that's probably correct. I need to think about this a little bit more. Yeah, we haven't thought very deeply about the edge physics, but that's
That may be an easier way to argue for the ground state degeneracy than looking at U1 level 8 and then braiding everything until you find something that
so that's what we did. We started with
Yeah,
one level 8. But you want to say the edge mode would be a more natural.
Yeah, I think you can probably think about the ground state degeneracy starting from the CFL evolving
Right,
CFL rather than evolving from more.
I think that that's a good idea.
Well, these density structure factors that you had at the table, so are those projected or are they total structure factors?
These are total structure factors.
If you go to the table that had all the stuff. I mean, the total structure factor of a gap state should start like Q squared.
Right. Okay. So yeah, of a gap state.
Yeah, like any translational invariant gap state in the Landau level should have Q squared.
Right. So here I'm just showing the non-analytic parts. So in a Landau level, there would be, let's say, some Q squared, which is completely universal.
Yes.
In the Chern band, there would be Q squared, but maybe non-universal.
So this is the next.
These are the non-analytic
Okay.
curves. I'm only interested in whether or not Fermi surfaces have.
Anyone else? If not, let's thank Pavel one more time. And you got 3 extra minutes of public break. We're back at 4:30. You're one. Yes. Stay here for 3 minutes. Oh, exactly. We don't have extra. Let me just
The number of momentum you have in the valley. And the way to do that is on the domain. This is where the action is. And then if the domain was IPC, basically. As long as the class of flow. That's very effective. Okay, and also
whatever this is not in the band base. It doesn't have in the band base, right? So then
yeah, I mean
there's a right. So this is where the Green's function appears. So this function is written in some different base, not in the band base.
I mean the separate issue
Orbital basis, not band basis, right? So
the plane base that's inside somewhere
kind of projected to the band. So I don't know if
maybe there's
so when you say that we should have both
Sure, 35 plus 5.
In what is
Yeah,
from here to go there.
Nice.
This P. Yeah. Okay, square root of P square root of P. No. Like square root of P can. We need to multiply P here also. Yeah, so the concept is
So, one announcement that I was asked to do. I'll have to make it again when more people arrive, but dinner is at 6:30, not at 6. If you go there at 6, they were not gonna let you in and they will yell at you, so. Our talk number 4 of the afternoon session is Jiabin. You remember the point, please.
All right, thank you. Thank the organizer very much for inviting me and for this nice opportunity for me to introduce our recent work, the quantum geometry perspective of correlated physics. This is a topic I've been working on for years, and the more I work on, the more surprises I got. And that's why I want to talk about it. And I use the word perspective, because I'm going to show you some intuition, some numerical result, and some proof, but it's far from a general theory. I think there's a lot of things to be done. Okay, first let's start with the acknowledgement. The work that we'll be talking about is mainly done by Awab. Is an undergrad student in my group. Now he's in Andrew's group, and Dean and Yuanzhuo from Michigan State, and the Princeton people, Mingxuan, Zhongnan, Park, Biao-Shensi, and Andrew. Okay. Let me start with the brief review of what quantum geometry is. Single particle part of the Hamiltonian we want to diagonalize under Born approximation. This is the periodic part of the block state, and this is the block Hamiltonian. And the geometric properties we normally talk about, quantum geometry refers to the gauge invariant change of the periodic part of block state when you change the block momentum or the change of the projection. Given a bands, it doesn't care whether it's topologically trivial or topologically non-trivial. You can always have some bands with strong geometric properties, but if it's topologically non-trivial, the geometric properties are bounded to be strong because, for example, if you have a non-zero chain number, you must have a singularity for the states and the winding, like the change of the state, periodic part of the block state has to be fast when you change the block momentum. This is the spirit of the topological lower bound of quantum metric. The conventional or classical geometric properties, geometric quantities, Berry curvature. Berry curvature has a specific momentum. Individual momentum is a geometric quantity. Like the integration of it is topological. Like this is sort of the distinction between geometry and topology. One is local, one is global. Okay. Quantum metric characterizes how fast the projector changes when you change the block momentum. And this is what we will focus on in this talk. There are two major properties of quantum metric that I think is quite relevant. One is the in real space, integration of quantum metric is basically the quadrupole density. Okay, the x is the x position operator minus the average value, and if you space it, it gives you the gauge invariant part of the spread of one-year function. And it's bounded from below by product invariant, right? As mentioned from in the last slide. And last slide was just the intuition. There is a specific expression, like for chain number, the integration of trees to quantum metric is just bounded from below by absolute value of chain number times 2 pi. And this chain bound was derived many years ago. If you really trace back to the history, like you can trace back to it's in the ... you can trace back to 70s when Polyakov studied nonlinear signal model. The energy is bounded from below by topological charge. It's the same bond, basically. But same bond has been there for a while, several years, more than 10 years, and people try to generalize it to other topological environments. And there is some straightforward generalization, but a real generalization was not present until last year. Together with Jonah and Andrew, we proved that any topological environment characterizable by Wilson loop winding bounds quantum metric from below, like this. It includes Kimberley Z2 index, inversion protected, flat topology, anything. Like even if like has second or Wilson winding, they all bound quantum metric from below. And this absolute value, just absolute value of Wilson loop winding. Okay, I might get back to this point later. Okay, this is basically the two major properties. And based on these two, you can already derive like expression that reveal the rules of quantum geometry or quantum metric in various physical responses. Like if you look at here, it's very much like optical response, because if you want to study the optical response, the perturbation you add is the electric field times position, and optical conductivity is basically the correlator of two positions, of course, it's time order. And you do the Fourier transformation, you immediately have this sum rule. Okay, and this sum rule is equals to the integration of trace two. But this sum rule actually is not very useful for experiments, because this goes from 0 frequency to infinite frequency. But recently there is some like resonant inelastic S3 scattering by assuming some parallel till in the dynamical structure factor, and can get some measurement of this quantity. Of course, as long as it's related to quantum metric, it's automatically bounded by topology from below. Okay, so and another response is supercurrent, and the superfluid weight, which is like is proportional to the integrated quantum metric. This is pioneered by Pavel's group, and they consider like flat band uniform pairing, and later on Andrew generalized to apply it to Tisibale graphene. This delta absolute value, just the amplitude of S3 pairing. And when I was in Maryland, Shankan and I also show that even for the Dipole pairing of Tisibale graphene, this bound still holds. Like this expression still holds. Just replace this amplitude by the average amplitude of the Dipole pairing over the brilliant zone, weighted by the quantum metric. Yes.
On the first one, the optical response.
Yeah.
So this integral over frequencies, this is essentially the imaginary part of the conductivity. Omega going to 0.
Yeah, but you need to divide it by 1. Like
you have one of them.
Yeah. Okay. Yeah.
So this is the imaginary part of the conductivity by
imaginary part of the conductivity. Yes, at static. Yes.
So if I don't have any G of K, so if I just have a trivial bands, set of trivial bands, I will not get any imaginary part of the conductivity.
If I understand your definition correctly, because I might not I might not be familiar with the terminology you use. I understand you use the conventional terminology. Then
Let me rephrase my question. If I have a set of trivial bands, I will not have a so G. What would G be for a set of trivial bands?
If it's trivial band, 0.
Like
parabolic band, 0.
So I would not have any any conductivity, any interband conductivity. Why?
Why? Okay, if you look at the interband matrix element, interband conductivity matrix element, it's like you have like U M like X U Y. I can write it like this, like U M. Actually, it's psi M X. Like M and N are different bands.
Yes.
This is the barrier connection. the off diagonal part of barrier connection. If you have a trivial band barrier connection 0, you cannot have this. You cannot have the even inner band. This if you integrate over the all frequency, this is the sum over all the inner band contribution basically.
Okay.
Yeah, I can show you the derivation later. Yes. Okay. There are other quantities related to the quantum metric, shift current, electrophoton coupling, and entanglement properties. Like I might also touch on this point later. And then this is a like growing community. Like recently, there are already several review papers. If you're interested, you can read them. Okay, this is just a brief review. Like let me just go on to the main topic. It's for the correlated phase. We will focus on this real space property first. Okay. Okay. In what angle I want to study the geometric perspective for correlated phases? This is the general Hamiltonian we normally study. Kinetic potential and density infraction are the bare Coulomb or square Coulomb, whatever. Like we often cannot start from this, right? There is always finite number of bands near Fermi level. If we project to those bands, the projected interaction will have a very special form. Like this is a one-band projected Hamiltonian. You have a kinetic energy part, and this special form of the projected interaction contains the information of the topology and geometry of the block states. And different topology and geometry give you different form and leads to different correlated phases. This is not new, like fractional quantum Hall. Projection of Coulomb interaction onto lambda level gave you this phenomenon, fractional chain projection of like square Coulomb onto the set of Murray bands. Like Coulomb interaction is everywhere. What is special is the geometrical topological properties of the low energy subspace you project it to. That is known. What I want to focus on is the topologically trivial case. I want to consider bands that is topologically trivial, but has very strong geometric properties. And if I have bands like this, if I do the projection, I have some sort of form of the projected interaction. What kind of phases it can give? I mean, let's first like what's so special about what's special about this kind of projection? It's nothing complicated. If you have a strong if you're trivial bands, it means you have exponentially localized one-year function. You have strong geometric property. It just means that your spread of the one-year function is very large, right? So if you have a weak geometric properties, the spread of one-year function is very small. Project any interaction on it, it's a local interaction. For strong property, geometric property, if you have longer range interaction, like if you start from multi-orbital local interacting Hamiltonian, you project a certain band with strong geometric property, this longer range interaction naturally would happen. And this is what we'll focus on. We will focus on what kind of correlated phases this kind of a longer range interaction can give you. So this will be a mathematical formulation of what I just said. Suppose you have like a lattice, each lattice side with multiple orbitals, alpha labeled by alpha beta. You can have density interaction among those orbitals. You do the projection, for example, to certain bands, and this band is characterized by a certain one-year function because we are talking about topological trivial bands. And you have this projected Hamiltonian and this projected form, like the form of the projected interaction is determined by the one-year function, basically. And let's be more concrete as a first example. Let's just consider a well-known model, this particle insulator model. Let's consider like each plaquette means like one lattice side. Don't try to treat those 4 dots in each plaquette as different sublattice at different positions. Just think of them at orbitals, 4 different orbitals on the same position. I just draw it like this just for you to visualize. Okay, and they have a coupling among them, and across different lattice size, you have hopping. Okay, and in the M much smaller than T limit, you have this nearly flat band. The dispersion of the band will be characterized by M, and the gap is characterized by T. And if you look at the lowest energy band, it will have a linear function centered not at the lattice side. It's obstructing atomic limit, not limit, obstructing atomic state. And with linear function, the leading order just involves these 4 orbitals like this. And of course, since M is this expression will be exact if M is 0. If M is not 0, you have like a tail that is dependent on M over T. Okay. So this is a model we consider. Now we add interaction to it. At the multi-orbital level, we add first the on-site orbital diagonal interaction. This was also used by Oscar and Andres' paper when they tried to study the anti-ferromagnetism, ferromagnetism competition because of geometry and hopping and half-fitting. But we also add an additional term that is between different orbitals, like alpha not equals beta. This labels the orbital index. And this is not some term that is new. Like in the ion-based superconductor community, this is widely used to describe this is one of the terms that people use to describe the magnetic properties. And if you're interested in it, you can read the review written by Andre. And just a side note, I learned about it because recently our experimental colleague shows that ion tellurium is actually a superconductor at low temperature, which was thought not as a superconductor for many years. And we use this kind of Hamiltonian to describe the transition between superconductivity and double stripe magnetic phase. Anyhow, so if you do the projection of this, yes.
Sorry. But then if you're going to use this term for consistency, you need also to include the Holmes and the pair hopping term.
Yes, yeah, the Holmes pair hopping term. You are talking about to preserve the SU2?
No, if you project, that's just Hubbard kind of more.
Yes.
U prime, JJ prime.
Yes, you prime, JJ prime. Of course, in this paper we include all of them. But for the simplicity, I said J and J prime equals 0.
But you can do that.
I know in reality I cannot do that. For this model study, let's just use this model. I mean, we can add more term, but it won't affect the physics. I guarantee you.
But the whole you're talking about ion-based superconductors, and we know Holmes coupling is one of the essential features.
Oh no! I was just seeing that this term has been widely used to study superconductor. I'm not using ion-based superconductor as an example. I'm just doing a model study. Yes.
Referring to the same question. Are you going to use U prime not equal to U?
Yes.
2 independent parameters. That's what Raphael was saying. That if U prime is not equal to U, J is related to U minus U prime, at least in ion-based.
Yeah, in ion-based, I totally agree. But I won't talk about ion-based superconductor. I just do a model study. It's just try to bear with it. It won't be related to the physics I'm talking about. We can add J, we can add J prime to do. You will get the same result. Okay. Okay, you do the projection of these two terms, and you will find an on-site term, and in the one-year basis, you will find this term will give you the nearest neighbor and next nearest neighbor hopping term. Of course, this is m equals 0 limit. If you if you include like m non-zero, which we do, you will have other term, but it's of order m over t. Okay, let's just take this model. I know it's not a suitable model for ion-based superconductor. Let's just take this model and study by projecting this on-site interaction to the band, what it will give you. And we did Hartree Fock away from half-fitting. We got ultramagnetic metal. Like basically, like it has a square root cell breaking, and within each cell, like in the reduced spin zone. And like the blue color is spin up, red color is spin down. You would have like the spin texture like this. So clearly, it breaks the half transition plus time reversal. It breaks the inversion times time reversal, and it preserves a C4 spin is C4 times spin for time reversal, and so and it's collinear. So it satisfies all the definitions of ultramagnetic state, and it has net magnetization equals 0. And these states, if we will consider a trivial atomic limit with very weak like geometric properties by doing the projection, we won't find it. And even if we do the unprojected calculation, because the parameter is actually in the projection range, projection region, like because U and T prime and M all much smaller than T, you will get the same results. And I'm not claiming that, like, because after projection, this is basically like Hubbard model with longer range interaction. We have nearest neighbor, next nearest neighbor. Actually, before this is ongoing work. Before our work, there has been a model with just Hubbard model plus just nearest neighbor interaction, and it has it shows it has stabilized the ultramagnetic phase. But in our model, even if we go beyond the projection limit, as the ultramagnetic phase is a stable phase, we can still have it. So this is what is this result beyond the previous work. Yes.
Can you explain the nodes here? Because I can see there are nodes along the diagonals, but there seems to be another nodal line that is not a high symmetry direction.
Which one? Which one?
The dashed line.
Like
the Brillouin zone, right?
The Brillouin zone.
There's clearly nodes along the diagonals, right? Because you change sign. But is this dashed line a nodal line?
This dashed line?
Yeah.
Although no, this dashed line is the edge of the Brillouin zone.
Oh, so you're plotting the reconstructed.
Yes. So this is the square root Brillouin zone.
But then, if you're breaking translational symmetry, why is this an outer magnet?
Because I mean, just like a Hubbard model, you break translational symmetry, you have antiferro, but that preserves the half transition, like in large unit cell, preserve half transition plus time reversal. This break it. This in the enlarged unit cell, this does not have any half transition plus time reversal, does not have any inversion plus time reversal.
Okay.
It satisfies the spin group definition of an ultramagnetic. Yes.
So ultramagnetism kind of appears when U is different than U prime.
Sorry.
So you see ultramagnetism when U is different than U prime.
That doesn't matter. Like
but U is equal to U prime.
Sorry.
Even if they are equal.
Yeah. Like the point is that the band you projected has to have strong geometric property. The band that at the Fermi has to have strong geometric property, and you have to dope it. If you don't dope it, we didn't find it. Okay. You may say that, like, there is a previous work with this longer range interaction. It's not that surprising, although we reframe it using this multi-orbital projected to bands with strong geometric properties. Like the next example, at least, is surprising for me. I mean, if it's not surprising to you, just let me know. Like, instead of thinking about repulsive interaction, let's talk about attractive interaction, right? Attractive interaction, like, again, you can consider multi-orbital model with on-site attraction, and you project it to a single band, and single like spin SU2 bands. And the model that in my mind is quite complicated. Let's just consider the projected limit. It has a form like this. So it's you can still think about the squared Hamiltonian, and U is negative because it's attraction, and you have the on-site density, you have the nearest neighbor density for W tilde, and this W tilde is not actually creation operator on each lattice site. It has a spread. So it has a W on the site and plus a weighted sum on the nearest neighbor. Okay, so this is the model we use. So you have a two spread, it's a density spread, and for the equation operator, you have also spread. We have two spread. And with this model, and this is the spin SU2 model, we can do auxiliary field. We consider like 3D and 2D on cubic and square lattice is sign problem free. We can do auxiliary field quantum Monte Carlo. We found dominating charge for you. Okay, and so this is the result for 3D, and the U over T is roughly minus 0.3, and so this is the spreading parameter we use, and we look at low density region. Like we consider like 1,000 lattice sites, 10 along each side, and the fermion number is 66. So this is basically the counting of how many, like the percentage of the fermions participating in S-wave parent, P-wave parent, and quartets chart for you. I need to know that. I need to note that the ground state, the metabolic ground state, is non-degenerate. I will have single ground state, spin singlet. So the P-wave parent is actually entangled pair, entangled double pair. It's entangled pair of P-wave parents to ensure the spin singlet nature. Okay, and this is the moment, like fermion momentum distribution participating in each channel. This is a total N of K. You have S wave, you have P wave, you have quartet here, and you can see that for quartet, it involves momentum with, it involves fermions with momentum quite far away from the Fermi momentum. Yes. Okay. Thanks. So we think this might be the parent of like the bounding state of parent density because it involves so many different momentum. It's very easy for a bounding state of two S-wave parent with opposite momentum to appear. Like this is basically what Yves was talking about. Yes, please.
Why the state wins over conventional S-wave as attractive interaction?
That's a very nice question. We don't understand, but I can tell you one thing. If we set this spreading parameter S, L, or S and L to 0, it's purely S-wave Tartui. So you can think about like this state has a very large, like this band has very large linear spread, and it feels like we sort of have a picture like because this parameter is somewhat close to BCS BC crossover, slightly on the BCS side. Maybe the S-wave parent is not that extended, and if you only have on-site, different S-wave parent does not really have enough attraction among each other and bound. Now we have the longer range interaction sort of bounded more closely, and they form a lower quartet condensate. That's the intuitive picture. Yes, please.
So if you dial down U, but still keep it attractive, will you gonna get an ordinary BCS state?
Nice question. We haven't tried it because this calculation is too demanding. Let me think.
It should just be Fermi liquid attractive.
Maybe. Yeah.
So then you get a phase transition between these two.
Yes. I think, okay. So that's another very good question. Okay. I'm not claiming, I only use the word dominating charge for you because we haven't done like serious finite size scaling to show that the S-wave, like the charge 2E channel actually decays to 0 as you go to larger size. We haven't confirmed this is actually a 4E thermodynamic physics. We're doing that right now, but I cannot claim it's a phase transition. Yeah. Yes.
The negative Hubbard-U model also has a CDW instability.
Yes.
So,
but not at this low.
So that's what I'm. So yeah. This is far from that.
Yeah. Okay. Yes.
And the other question is, there's an old paper by Nozier where it says that to have a pair of bosons, which would be a quartet, you need to have two different species of bosons. So in superconducting language, you need to have more than one condensate to stabilize a quartet.
Yes.
Is that the P and S that is doing the job?
Yeah, I think so.
I see.
We had a effective field theory. I don't think the effective field theory is derived very like explicitly, but there's the picture, right? These two condensates actually assist each other to help like the P wave. Okay, let me tell you this. When I set one of the parameters to 0, P wave quartet disappears simultaneously. They appear simultaneously, and disappear simultaneously. The P wave channel interaction definitely assists the S wave to bond together. Yeah. Okay. In 2D, they also tested, but they didn't test much enough. But there is a chart for each channel, but it's not dominating yet. We are doing more search in the parameter space. I mean, I will tell you why they care about 3D so much later. So I guess I don't have much time, but let me go through it quickly. So why we care, or why we think this SU2 model given quartet is somewhat interesting, because like recently there have been many, including auxiliary field quantum Monte Carlo study on SU4 model. For SU4 model, the chart 2E is sort of banned from symmetry if you assume a single many-body state, because two particles just cannot form a SU4 singlet, right? So you are, if you have a non-degenerate many-body ground state at fixed particle number, you are bound to have, and you have a condensate, you're bound to have a 4E condensate. Okay, but for SU2 model, as I just mentioned before, this longer range interaction is definitely important, or the geometric properties of the projected band is definitely important, but we haven't checked whether it's thermodynamic phase of chart 4 or not. We need to do more finite size scaling. And moreover, like you may ask why we care about this chart 4 force, like if phase. I mean, it's a conceptually exotic phase, and it might be related to high TC. But let me provide you another reason to care about charge 4E. It's neutron matter. It's neutron star. Yes, it's actually true. I'm gonna convince you why charge 4E gonna happen, not charge 4E, quartet gonna happen in neutron matter. Okay. So first of all, I can tell you, neutron matter, there is experimental evidence showing that neutron matter has indirect evidence, has attractive interaction among some channel. Okay, so if you look at a pulsar, what is pulsar? It's a neutron star with a radio beam, and it spins very quickly, and the spin axis normally is not the same as the radio axis. So that's why you can see, right? You can see the frequency. And there is a phenomenon called pulsar glitch, where the spin frequency suddenly change by a finite amount, not non-zero amount. And those people, nuclear people, astronomers, they try to explain it for a very long time. The most accepted explanation for this pulsar glitch is that inside neutron star is actually a superfluid, and it has vortices. And the vortices are pinned, and when it's got unpinned, it will change the frequency by a quantized amount. This is their consensus. But maybe you think this is too indirect, too imaginary. Let me give you a tabletop evidence for like quartet bound state. If you look at the matter bonding state, bonding energy of helium-6, helium-4, helium-8, you subtract helium-6 bound energy by helium-4 bound energy, you get 0.9. You subtract bound energy of helium-8 minus by helium-6, you get 2.14. It means that when you have two pairs of neutrons, it's just like like the energy they release, it's not like forming two independent pairs. They actually bound them and release more energy. So this is a clear evidence of like quartet bonding in nuclear matter. And my collaborators also found the similar phenomenon of oxygen and for some other elements, and they actually did the calculation with the effective field theory from the QCD interaction to the fourth order, and they found the attraction in S wave P wave channel, and they can get a number very closely. Yes.
So is superfluid helium-4 an example of a proton/neutron quartet that is a superfluid?
When we say superfluid helium-4,
BEC regime.
yeah, we are talking about a superfluid of helium-4, right?
Helium-4 is just 4 protons.
But
2 protons, 2 neutrons.
I understand, but that is not due to nuclear force. I'm just right. Helium-4 condensate is not due to nuclear force, right?
The pairing is, but yeah.
The pairing is?
The nucleus of the helium.
Okay. Inside helium-4 is. I'm talking about the superfluid due to nuclear force, due to QCD, not QED. Okay.
It's also, I think it's just an ultra BEC version of what you're talking about.
Okay. All right. Well, we can chat about that later. Anyhow, yeah. So I'm telling you, like, what you are doing, also, although you are doing condensed matter, your work will be important for neutron stars, for those large galaxies, large bodies in the universe. Okay. So don't underestimate your work. Okay. All right. So this is strong geometry for that longer range interaction, and you have some interesting correlated phases. Like, of course, this is just intuition numerical results. I don't have time to go. How much time do I have?
0.
Okay, I'm gonna take -2 minutes to see something else. Okay, quantum geometry also reflects in correlated charge fluctuation. Let's not worry about that. Okay, I just want to see that. Want to get along, like, closer to the trend of this workshop. Long's experiment shows Vena crystal in rhombohedral folia graphene, and like in a range of the discriminant field and in the density. Like, we recently did some this ongoing work, studied the nematicity of this Vena crystal phase. I mean, like, in my mind, it bound to have, like, some Vena crystal phase in this example, in this experiment has to be nematic, because, like, Liu found nematic metal in 6 years, and 4 years, 6 years, I don't see huge difference. Like, if you lower the temperature starting from a nematic metal, if you crystallize, you're gonna find nematic Vena crystal. Like, this is the intuition, right? So we did the Hartree-Fock, like, my postdoc Yang led this effort. We did the Hartree-Fock calculation. I know there's a lot of controversy about Hartree-Fock, whether it's civilized or not, right? Let's we indeed find nematic Vena crystal. Like, this is the real space density, which it actually has a gap of 14 MeV, and the physical picture is quite straightforward. If you look at the Fermi sea at this parameter point, and just for a peaceful mind of some audience some people in the audience, we tried both hard neutrality scheme and average scheme. They both show the same phenomena. So if you look at the non-interacting Fermi sea, it has a shape like this, right? And for the nematic Vena crystal, it basically occupies one of it. This is the occupation distribution of a nematic Vena crystal phase, and these two reciprocal lattice vector is actually the right one for the unit cell at this nematic Vena crystal, and you can clearly squeeze them into this Fermi sea, like, from boundary to boundary. But if you want to like, squeeze the reciprocal lattice vector for C3 symmetric Vena crystal as the same density, you have to populate a large amount of high energy modes to do that. That's why it has a higher energy. Anyhow, I'm gonna stop. Okay, one last sentence. If you listen to Alan McDonald's talk, you will find this is similar to what he said. I didn't know that. So after his talk, I already emailed him. Like, clearly our work has some overlap with his work. Okay, thanks.
Questions? You know, how is the real space
configuration of that ultramagnetic phase?
Oh, it's
Is it easy to sketch?
yeah. Basically, I think so. You have square root. Basically, basically like this. Sorry. Yeah, if you look like it, it's like a antiferromagnetism, but it has some. Yeah, it's basically look at it, but it has some inner structure to guarantee that the half translation plus time also does not is not preserved.
So is this in the L state? Sorry,
Sorry. Oh, sorry.
This is in the L state.
No.
But if it's now on the square lattice.
No. It has some inner structure inside. So I'm just plotting on the linear function. It has some inner structure.
Orbital degree.
Yes. You can, because now you have sublattice. You have some bounding in the sublattice.
Okay.
Yeah. We can
talk with this.
Nishan can show you the structure. Okay. Yes, please.
Yes.
Maybe I will ask for the same question. In terms of this is a real space picture.
Yes.
In momentum space.
Yes.
Is your order antiferromagnetic order with extra d waveform factors?
Yes.
So it's just like you take c dagger k plus
yes.
q over 2 ck minus q over 2 spin, and then multiply by a function f of k.
Exactly. Yeah. You can essentially think about that. Like that.
Very quickly.
Yes.
Story about pneumatic state near Wigner crystal is very interesting.
Yeah.
Is there any experimental evidence that when quantum oscillations detect large Fermi surface,
okay,
that this Fermi surface has some pneumatic properties in it?
Okay, so this the Wigner crystal I'm talking about is insulating. Are you talking about metallic Wigner crystal or insulating Wigner crystal?
Well, I'm talking about measurements of larger Fermi surface in BBG, RTG, etc. Because evidence for pneumaticity there is when the out of 3 small pockets, 2 disappear or 1 disappear.
I see.
So evidence that large Fermi surface also has some disappearing pieces.
I'm not sure about that, so I don't know the answer to your question. The measurement in my mind is that it's like it Lewis sunflower setup. You strike current, and you look at the critical current, and different direction the critical current is different. That's the possible verification in my mind. Okay.
More questions? Yes.
Yes.
In your calculation to say the charge 4E, condensate, is that finite temperature calculation?
We try to convert to very low temperature. We try to convert to 0 temperature. Of course, it's always finite temperature calculation. We try to increase the imaginary temperature to a very large, beta to very large value.
So then in this case, what in the lowest possible temperature you can do this calculation? What's the lowest temperature?
So it's so the 1 over the KBT divided by parent is 1 over 30. 1 over 30. Yeah.
So
yes,
let me make 2 statements and ask you to make a third statement. So how do I get a exact ferromagnet? I project to a band that's SU2 that's got quantum geometry and integer fillet. And then with repulsive interaction, the quantum geometry is the spin wave stiffness. I get a good exact ferromagnet. How do I get an antiferromagnet? I project to a band without quantum geometry, and I get a TJ model. Now, do you have the similar statement about the ultramagnet?
Not right now, because that's a very good question. We dope the wave from half filling, and so we currently don't have a very good picture. That's why I said in the beginning I have intuition, calculation, and some proof which I didn't have time to show, but we don't have understanding like that.
Thanks.
So what did you compute when you were talking about the charge 4E?
We can compute first of all to confirm the order exists. We compute off-diagonal long-range order, and we can also count the number of pairs, SU pairs, PV pairs, and a number of quartets by by compute the average value of the corresponding cumulant. Yeah. For example, for quartet, we have the correlation function. We subset all the one body contribution, two bodies, three body, and we compute the average value. Okay. Yeah.
Time for one last question. Yes.
Yeah. So just a general question. So what do you mean by like strong quantum geometry? How it's related to like properties of the matrix J that you defined?
Very large. Just G.
Okay, so I can,
if you integrate
compute this matrix.
Yeah.
And
yes. If
but
you,
as far as I understand, like, I mean, you don't have like a very curvature, so they are like topologically trivial.
well, I can have Berry curvature, but just like the integration of Berry curvature over the Brillouin zone equals 0.
Okay, so but so you know what properties of this matrix G are interesting or
so are what? So what property of the G are? Sorry, I didn't hear clear your question.
Yeah, again, like what do you mean by strong quantum geometry?
Oh, you take the quantum metric, take the trace, integrate over the Brillouin zone.
Okay.
You get a value, right? Large value means strong. Small value means weak.
It's like you compute integral over A of trace G.
Yeah.
And you said it should be 0 because like it's
No.
integral over.
The integrated of Berry curvature is 0. Trace G is not 0.
Oh, okay.
Yeah.
It's a different thing.
Yes, it's two different things. Yeah.
And you said it's related to like conductance or like
Optical conductivity is related to optical
like
conductivity.
not sigma xy but sigma xx and like
It's all
because sigma xy is a Chern number, right?
yes. The sigma xx, sigma yy. Yeah. But sigma xy with 0 frequency, like the static sigma xy is Chern number. And if you look at the optical part, the symmetric, you can still get a symmetric part.
But it's not quantized.
It's not quantized. It's not quantized.
All right. Let's take the speaker one more time. Right, and the last speaker today is Kwan.
All right, so let me thank the organizers for putting together this nice workshop and for inviting me to give a talk. So unlike Jiabin, I won't be talking about neutron stars. My talk will be very down to earth. I'll be talking about rhombohedral graphene. And in particular, I will discuss a model Hamiltonian that we've given the very endearing name, the Berry Trashcan. And this is designed to capture the confluence of energy, correlations, and topology that in this material that we've talked about a lot so far during this conference. And I'll walk us through some examples of how this model we think can provide some analytic insight into interesting phases such as Wigner crystals and chiral superconductors. So before I continue, let me acknowledge my collaborators, in particular with Andrei Bernovic. We developed this model while also at Princeton, and we did the calculations on the Wigner crystals. And later on, we were joined by Hong Yao and in particular Ming-Ray Li on the superconducting side of things. So this is an outline for my talk. I'm going to begin by just motivating how we can construct this Berry Trashcan from thinking about the rhombohedral graphene Hamiltonian, just for those who have not seen this model before. And then I will discuss two case studies showcasing how this model can provide a tractable starting point for thinking about interesting phases that have been proposed to be relevant in this material. So let me start up here by talking about the material and the model. And we've heard a lot about rhombohedral graphene already, so I can be quick here, but let me just specify exactly what we're looking at today, right? We'll be interested in the regime of electron doping and a strong displacement field. And as long has demonstrated, the phenomenology here bifurcates depending on whether you have HV alignment or not, right? So, for instance, if you have HV alignment, as Jonah emphasized, this is a Moire heterostructure, and you find things like integer and fractional turn insulators. But if you don't have the alignment, you instead find these superconducting pockets, which are unconventional in certain ways. So, for instance, the normal state exhibits some amount of anomalous Hall effect and is believed widely to be some sort of spin and polarized quarter metal. Furthermore, there's hysteresis within the superconductor, which points towards a time reversal breaking and potentially chiral superconductor. And yesterday, Ellie also told us about some interesting magnetization within the superconductor. So clearly lots of very interesting going on in this material. So it behooves us to try and theoretically understand what's going on and to extract, at least in broad strokes, what the important ingredients are. So to do that, let me just say a few things about band structure. So as we heard a lot, one very important thing about these devices is that you can tune the band structure using a displacement field, as shown here. But this band structure was computed with, a microscopic Hamiltonian with many different terms and hoppings, etc. I think there's at least 8 independent parameters in the full model. So it's a little bit tricky sometimes to understand exactly what's going on. So to help us build some intuition, it's useful to start from a simplified treatment, and we'll see how this will segue into the buried trash can. So I think as Jonah already mentioned this morning, the dominant terms in the single particle Hamiltonian are the intralayer Dirac term, which has a scale of Vf times k, and the nearest neighbor interlayer hopping, which has a scale of T1, right? And rhombohedral stacking you could think of as looking a little bit like a finite SSH chain. And so if you're at small momenta near the Dirac point, then you're in the topological phase. You should expect to find low energy edge modes, two edge modes, which are actually really the surface states, right? And all of the interesting physics happens within this sort of surface states, right? And of course, when you go to large momentum, right, you're in the trivial region, right? And so you expect to lose these low energy modes, and your kinetic energy should therefore blow up, right? And indeed, if you just do a slightly more quantitative analysis of these surface states, you indeed find, as we've heard before, that the dispersion of these states is some higher order, nth order Dirac cone, where n, so k to the power n, where n is the number of layers. But crucially, this band structure still has no Berry curvature. The reason is that we have a combination of 3D inversion and time reversal symmetry, which forbids a Berry curvature. But this can all be remedied if you apply a displacement field, which does 2 things, right? So first, it splits these surface states into valence and conduction bands. This opens a large gap at neutrality, and it flattens the conduction band edge, so leads to a high density of states. And furthermore, because we've broken the symmetry, you can therefore generate a finite Berry curvature, right, at low energies, and this is critical for enabling topological and anomalous Hall physics. Okay, so in this work, we introduced a model called the Berry trash can, which is meant to capture the salient features of this situation. So there are 3 steps here. For the first step, we're going to project into, say, the conduction band, right? So there's a huge gap here, so we can sort of ignore this band. And we're going to choose the conduction band because that's relevant for electron doping experiments. And we're going to further restrict to a single spin and valley flavor. The idea is that at low densities, we can expect interactions to drive flat band ferromagnetism, basically. For the second step, we're going to further simplify, and we're going to model the dispersion with this shape. So we're going to model the surface states with a completely flat disk or circle with a radius of kb. And this is going to be surrounded by very steep walls with some velocity v, right? So basically, we're taking the dispersion and we're replacing it with a trash can shape like that. Good. But of course, specifying the dispersion is not everything, right? There's a lot of information that's encoded within the Berry curvature and, as Jiabin mentioned, the quantum geometry. And if you expand near low momenta, you find that actually the overlaps of the block functions, in other words, the form factors, they approximately obey the so-called Gervin-McDonald-Platzman algebra of the lowest lambda level. So for the third step, what we're going to do is we're going to replace the form factors for all momenta precisely by this GMP algebra, as shown here. And what this does is that this encodes, therefore, a uniform Berry curvature, as shown over here. And the Berry curvature is simply 2 times beta. Beta is a parameter that we're to introduce. And beta is just nothing more than VF squared divided by T1 squared. So to summarize, this is the general form of this Hamiltonian, right? Gamma dagger K is just the creation operator for electron in this band now. E of K is just this dispersion with this shape. And to this, we're going to add a density-density interaction with some interaction potential V of Q, right? And the quantum geometry of this band is encoded within these form factors MKQ. So this is encoding these GMP form factors. Yeah.
Does the actual one also, does it have a peak around this range?
Good. So the real if you look at the actual model of one meter there is like a, so if you look at the quantum geometry, it does have a peak at the edge, right?
Yeah.
Here we're just treating it completely flat. That's right. Yep. So in principle, the interaction potential V of Q could be anything. But for later analytical progress, we're going to restrict to an exponential interaction where V of Q is proportional to e to the minus alpha Q squared. So I've introduced another parameter, which is alpha, that just sets the decay scale of the interaction. And yeah, it fits well to Coulomb if you have a short gate distance. And let me finally say something about the symmetry of the model. So I'm not going to put any Morey terms here. So this model exhibits a continuous translation symmetry. And because of the circular nature of the dispersion and the isotropy of the GMP, this model also has an emergent full SO2 rotation symmetry, which will be quite useful later for us. So that's the model. And with that introduction, we've seen now how we can construct this Berry Trashcan. Let me move to the first example of some interesting phase that we can treat in the system, which are Wigner crystals. Okay, so to motivate the problem, let me just remind us of what happens in the standard 2D electron gas, right? So there, it's known that for sufficiently low densities, when RS is sufficiently large, right, interactions become significant. And what happens is the system will minimize the Coulomb repulsion by arranging the electrons into a triangular Wigner crystal. So like as shown here. And Wigner crystallization has also been proposed to be relevant for now and rhombic hydrographene. But I can see, but from this picture, the situation here differs from the standard 2D gas in some important ways. So first of all, the dispersion in these systems is usually far from parabolic, right? And second of all, the Berry curvature intrinsic to the block functions can potentially drive new types of Wigner crystals, right? So one possibility, for instance, is that the Wigner crystal could be topologically non-trivial, right? We do have some Berry curvature. It could have a non-zero Chern number, and these have been known as anomalous Hall crystals. So in this work, our goal was to sort of try and understand the phase diagram or the energetic competition between these different types of Wigner crystals in this Berry Trashcan model. And our aim was to try and get some analytical understanding. So to do that, we focused on the following specific setting. So what we did was we performed an analytical Hartree-Fock study of Wigner crystals at so-called full filling, right? So full filling means that I have roughly enough electrons to fill just the bottom bit of the flat part of the Trashcan. The reason is that, if your density is much larger than that, well, your chemical potential will be in the very steep region. Your density states will be lower, and so maybe crystallization isn't as favored. And if your density is much smaller, which actually may be more experimentally relevant, you have to contend with a very large degeneracy of single particle states. So the mean field will be harder, and fluctuations may also be important. So we picked full filling to strike a nice balance between these two regimes. Now, of course, a Wigner crystal spontaneously breaks the continuous translation symmetry. So an electron is now, its momentum is now conserved only up to a reciprocal lattice vector, G, of the Wigner crystal Brouillon zone, right? And so I'm going to be considering crystals with hexagonal symmetry. So I'm going to preserve the intrinsic rotations of the rhombohedral. So that means that my Wigner crystal Brouillon zone is a hexagon, which is this sort of thick hexagon over here. And I'm going to introduce an important parameter, which is what we call phi. Phi BZ, this is known as the Berry flux, and this encodes the amount of Berry curvature that's sort of captured within the first Brouillon zone, or roughly the Berry curvature within the flat part of the trash can. And to make our lives easier, in this analysis, what we can also do is, because of the very high kinetic penalty of the states on the walls, we can also impose a very tight momentum cutoff around the first Brouillon zone. So in this mean field analysis, we can just include states within these gray shaded regions. Okay, and just a few more technical comments, right? So the momenta in the Brouillon zone will, or momentum space will divide into different regions depending on how many partners they have within the cutoff. So for instance, if I just think about a plane wave near the center of the Brouillon zone, well, it has no partners because if you try and jump by a reciprocal lattice vector, you immediately leave the cutoff. So these momenta are actually easy to treat in our work, because if you want an insulating Wigner crystal with 1 electron per unit cell, you're going to fill these states, right? On the other hand, if you have a momentum near the straight edge of the Brouillon zone, these have 1 partner. So for instance, this guy and this guy can hybridize within the Wigner crystal. And these regions form what we call slivers, these blue rectangles. And last but not least, we also have the regions near the corners of the Brouillon zone. These have 2 other partners. So, this guy can talk to this guy, which can talk to this guy. And these form what we call patches, which are these yellow circles. And these slivers and patches are actually quite tricky to handle within our analysis, because what we have to do is we'll have to figure out the Wigner crystal order parameter within these regions. And this order parameter can vary non-trivially with momentum. In particular, if you have like an anomalous Hall crystal of some sort, these order parameters will wind with some non-trivial phases. Fortunately, I'll spare you the details of the analysis, right? We have a rather long appendix, right? But it's hard to find ultimately, and we're able to solve these equations, right? So let me just summarize the results that we managed to obtain analytically in certain limits. So remember, we're trying to compare the energies of different types of Wigner crystals in our model. And Hartree-Fock means that there's a Hartree term and a Fock term. And generally speaking, we expect the Fock term to be the more important term compared to Hartree. The reason is because the Hartree term only acts at a momentum transfer of G, which is the reciprocal lattice vector. This is a large momentum, and this contribution will be suppressed because of the decay of the form factors and the decay of the interaction potential. So as a first treatment, we can think about just the Fock term first, and we can add the Hartree later. And so if you only keep the Fock term, this is a summary of our phase diagram. So the horizontal axis here is just the Berry flux, which is the amount of Berry phase enclosed within the Brouillon zone. And basically, the picture is very simple. What you do is you take your Berry flux and you just round it to the nearest multiple of 2 pi. And that tells you the Chern number of your Wigner crystal. So for instance, if you start from phi equals to 0, that means you have completely trivial bands, right? Not surprisingly, you have a trivial Wigner crystal. But as you crank up the Berry curvature, or the Berry flux, you hit a transition when you reach pi, and then you click to the Chern 1 state. And this continues. So as you further increase your Berry flux, you go for Chern 1, Chern 2, Chern 3, and so on and so forth. Right. And this sort of principle has also been dubbed as Berry curvature rounding. So this is quite well, at least in this model, we've proved this principle in this particular model, right? So the Berry flux plays a very important role in the topology of the resulting Wigner crystal. We can also add back the Hartree contribution. Basically, the Hartree term will penalize the different crystals depending on the electrostatics, right? They will penalize states that have a very strong charge modulation. And let me just focus on a restricted region where phi is between 0 and 2 pi. The reason is because if you actually look at actual rhombohedrographene, the amount of Berry flux is usually around 0.8 to pi, right? 0.8 pi to pi, so within this range. And basically, what happens is that the Hartree term actually disfavors the turn 0 state relative to the normal Hall crystal. So basically, you initially have a phase boundary at pi, but as you increase this Hartree contribution, this phase boundary migrates to the left, right? And this is controlled by the Hartree strength, which you can think of as being controlled by, for instance, the gate distance. Good. So that's the summary for this part. So I've shown you how the Berry Trashcan can provide a analytical limit to understand Hartree-Fock-Wigner crystals at full filling of the Berry Trashcan, and we've highlighted the crucial role that the Berry flux plays in this system. Looking beyond, we're looking at other situations. For instance, what happens beyond below full filling, right? Which is perhaps more experimentally relevant. Let me also quickly advertise this experimental collaboration with Xiaobo, where we showed that actually in many of these rhombohedrographene systems, even at integer filling, beyond mean field fluctuations actually appear to play a qualitative role in the phase diagram, right? So all the stuff I mentioned just now was mean field, but we should always keep at the back of our minds the potential for quantum fluctuations to not just have a quantitative effect, but even change the phase diagram qualitatively. So if you're interested, you can have a look at this paper. Okay, but with the time I have left, I want to switch gears and talk about something a little bit more modern, which is superconductivity, right? And this is motivated by these experiments of these superconducting pockets that we heard a lot about yesterday. So as a reminder, this is what the Berry Trashcan Hamiltonian looks like, right? And we want to access superconductivity analytically in some way, right? So to do that, I'm going to make two approximations to this model. The first is I'm going to take the walls of the Trashcan and I'm going to make them infinitely steep, right? I'm going to set V to infinity. So this flat region still has zero kinetic energy, but I'm going to prohibit my electrons from venturing further beyond this. And the second thing is also a pretty drastic approximation. We're just going to put in an on-site attraction by hand. So this is going to be an on-site delta function attraction. So in momentum space, our V of Q is just a negative constant U. And as we'll see with these two conditions, we can actually access the many-body ground state analytically. And so then we can answer for this system, does the system superconduct? And if so, what is the pairing symmetry of the superconductor? So as a warm-up, we can first deal with the two-body problem, right? Do two electrons form a bound state? So because I have translation symmetry, I can restrict to zero momentum pairs with plus k minus k. It turns out the finite momentum pairs have a higher energy, so I can ignore those. And because of the SO2 rotational symmetry, the relative angular momentum, m, is a good quantum number, right? So I can decompose my Hamiltonian into these angular momentum channels. And whichever channel has the lowest energy state should probably dictate the pairing symmetry of the superconductor. And if you do this projection, right, so I'm just taking the two-body Hamiltonian and I'm looking at different angular momentum sectors, we find something quite interesting, which is that the Hamiltonian actually vanishes unless the relative angular momentum m of the pair has the same sign as beta, which is nothing more than the Berry curvature, right? So if they're opposite signs, the Hamiltonian vanishes, and in the active channels where they're of the same sign, we further find that the Hamiltonian has rank 1. So what this means is that within each channel, there's actually only one non-zero energy state. Its energy is actually negative, not surprising. It's an attractive problem. All the other states in the two-body Hilbert space are exact zeros. So this simplifies the problem quite a lot. So this is the, let me call E2 the energy of this pair wave function for angular momentum m, and let me denote O2 dagger as the creation operator for this pair, right? And because we have a short range attraction, right, you may anticipate that the ground state should be in the lowest angular momentum m equals to +1 or -1 channel. And indeed, if you look at the explicit solution, I mean, you can't see it from here, but if you analyze the expression, we do indeed find that the lowest energy state is in px plus or minus IPY. But I want to emphasize this notion of chirality locking, which is that let's say if the Berry curvature beta is positive, then this stabilizes the m equals to +1 pair, right? Or in other words, the px plus IPY pair. So basically, the chirality of the pair is locked to the topology of the underlying band. Good. Great. So, okay, but these are two body states, right? And superconductivity is a many-body phenomenon, right? So is it possible to build some many-body condensate out of these P plus IP pairs? And happily, the answer is yes. So what we discover is that our Hamiltonian, at least approximately, obeys something known as a restricted spectrum generating algebra, or SGA for short. So this has been introduced in the context of quantum scars. And our Hamiltonian obeys an RSGA of level 1. What this means is that you have this sort of ladder-like commutation relation between the Hamiltonian and the pair creation operator, but only if you're acting on the vacuum state, right? So you have this condition, and this eigenvalue is nothing more than the pair energy. And furthermore, the higher order nested commutators of H and this pair creation operator, they all vanish, right? So this is what defines this sort of algebra. And if you're given these two conditions, you can show quite easily that you can build a tower of many-body eigenstates just like this. So what you do is you take your vacuum, no electrons in it, and you just repeatedly act on it with O2 dagger, right? So you keep creating P plus IP pairs, and the energy is simply n, the number of pairs, times the pair energy, E2. Now, strictly speaking, this algebra is only satisfied to leading order in the Berry flux in this sort of quantity. But fortunately, if we think about the realistic system in rhombohedral graphene, 4, 5, 6 layers, this quantity, depending on parameters, is only around 0.25 to 0.35, depending on what precise hopping parameters you use. So we can anticipate that this correction hopefully is quite small, and we'll check that later. So anyway, we have this, because of this algebra, we now have access to these many-body wave functions, which should be eigenstates of the Hamiltonian. But of course, one should ask, is it the ground state of the Hamiltonian? And happily, the answer again is yes, right? So what we're able to do is we were able to massage the Hamiltonian to the same order in beta and rewrite it as a positive sum of squares, this term over here. U is negative, so it's positive, plus some constant as shown here. And so therefore, the many-body energy of this Hamiltonian is strictly lower bounded by whatever this constant is. But this constant is nothing more than, so any is the number of particles, so this is the number of pairs that you have. This is nothing more than the number of pairs times this two-body energy, right? And our tower of states for 2 particles, 4 particles, 6 particles, it precisely has that energy. It precisely saturates this bound. So therefore, we know that, at least in this limit, our eigenstates are actually ground states as well. right? So therefore, now we have a pretty clean ansatz for the ground state. For even electron number, we just hit the vacuum with our P plus IP operator many times, right? As shown over here. And for odd electron number, it's not that much more complicated. We hit it with the pair operator, and we just add an additional electron, an additional unpaired electron at zero momentum, at the Dirac momentum. So we've benchmarked this ansatz with numerics, right? So here I'm showing exact ionization calculations on 31 sites as a function of the filling factor in this trash can. So we go all the way from empty filling all the way to full filling. And we've verified that the overlap of the numerical ground state with the ansatz is very high. So for instance, for all even particle numbers, the overlap remains above 98%. And for all odd particle numbers, it remains above 98% for even and above 95% for odd particle numbers. And we've even checked that even if you perturb away from this solvable limit, so for instance, we started with a strictly on-site interaction, but you can also consider a finite range interaction, and the overlap remains very high. So we think that this sort of ansatz is quite a robust ansatz for this Hamiltonian. And we can also check some other things just to be sure whether we're really dealing with a superconductor. So for instance, we can check the binding energies just by looking at the many-body spectrum. The paired binding energy, which is just looking at E of n minus 1 plus E of n plus 1 minus 2 of E of n. It shows this characteristic even odd effect, the staggering effect, which demonstrates that electrons are making pairs. And this seems to be well converged with system size. And finally, we also checked the quartet binding energy. So we heard about charge 4e. In this case, we can show that our Cooper pairs do not clump into 4e groups. So this does show that indeed we do have a paired wave function. And second, and most important, we also checked for phase coherence by computing the checking for off-diagonal long-range order, or ODLR, right? So basically what we do is we compute the two-particle density matrix and we diagonalize it in this channel. And so the left plot shows that the dominant eigenvector, the eigenvalue, scales with the particle number, right? And this is precisely what you expect in a superconductor, right? Again, pretty well converged. And we can also analyze the pairing wave function, again, by looking at the dominant eigenvector of the density matrix. So this is what I've shown the phase of that over here. And maybe it's hard to see the colors, but what you can see is that the phase winds by 2 pi as you go around the middle. And so this is indeed an m equals to +1 or a p plus IP superconductor, right? So I think we've shown quite convincingly that this is indeed the case. And so that brings me to the summary of this part, which is we've shown how this buried trash can provide an analytical limit of chiral superconductivity in a model motivated by rhombohedral graphene. And we've emphasized the interesting fact that the chirality of this pair is locked to the buried curvature of the underlying band. And we're currently trying to add some more bells and whistles. So for instance, this is a pretty extreme approximation, right? And we can think about adding things like a finite velocity of the wall, trigonal warping, and other corrections. But there is one other big open question, which is what is the mechanism for the attraction? And I think this is a question more generally beyond just our model. We just added an attraction by hand, but where is it really coming from in reality, right? Is it phonons? Is it screening? Is it some weird collective mode fluctuations? I think that's still to be addressed. So let me end with some concluding remarks. So I've shown you how we can motivate this buried trash can from thinking about the physics of rhombohedral graphene. And I've showcased 2 examples of correlated and topological phases, symmetry broken and topological phases, Whitney crystals and chiral superconductivity. We're not stopping there. So we're actually looking in some other regions as well. So for instance, with Andreas and others, we're thinking about the repulsive side again, but we're trying to look for exact states as well, analytical states. And so far, right, we've managed to find some interesting results. For instance, there's a manifold of zero energy states, and we're still trying to figure out exactly what these means in terms of either order or whatever it means, right? And with others, including Jonah here, we're also thinking about the collective modes of these sorts of states. This will be important for thinking about the dynamics of these phases, as well as things like quantum fluctuations and whatnot. So I would say stay tuned for updates, and thank you for listening.
Sense about how big the superfluid stiffness is it set by beta and U, or?
So it's actually a bit tricky because so we took this approximation where the velocity is infinite. And in this case, some of the calculations are actually somewhat singular, so the stiffness is actually tricky in this limit. So we're working on that. But I anticipate that it will be set by, well, if beta is 0, then the superconductor vanishes, right? So beta will appear in there somehow, but the velocity should also enter in some non-trivial way. But I don't know exactly how it pans out yet.
Really?
Pretty much the same question, but about different latitude. Suppose I just look not on the stiffness, but on superconducting gap order parameter, of diagonal order parameter.
Good.
That scales with beta times U.
So actually, it does not. So one important thing about our analysis is that for at least for the superconducting side, is that at least for the analytics, right, this is controlled actually for relatively small beta, right? And what we've seen is, you could ask in our okay, let's say you don't want to you want to venture further and think about large beta, right, or large U, for instance. In the case that U doesn't matter because our we don't have a kinetic energy scale, right? But let's say large beta, right? In this case, we actually find numerically that so for small beta, so if the Berry flux is around less than pi, roughly speaking, these results match very well, and we get a gap, etc. Right? I forget the precise scaling, but actually, if you increase your Berry flux too much, so if you start to approach 2 pi, roughly speaking, we actually find that the spectrum no longer resembles a superconductor. So whether or not that's finite size effects or not, that's not completely clear, but certainly it has to be non-monotonic because it vanishes at beta equals 0, and it seems to go away at large beta as well.
Alex?
For the superconducting part, what is dependent from feeding flux?
Good. So in terms of the, let's see, I think might have some thoughts here. So I think the amplitude is actually strongest near dilute filling, and it sort of smoothly vanishes as you go towards full filling.
So would that hard cutoff in momentum give me some Vidal oscillations in the pair wave function, something like that?
Good, that's right. So one very funny thing about the pair wave function is that if you actually look at, let's say you want to ask, say, how does it decay with distance, right? So for a strong pairing, it should be exponential. For weak pairing, it should be 1/r, right? So we actually find something in between, which is a bit strange. There's actually 1/r to the 3/2. And there are indeed oscillations, but at least the decay is 1/1 divided by r to the 3/2. So again, that likely comes from the hard cutoff, right? So once we relax that, then we'll have to see exactly how that pans out.
So two things. So first, so here you're plotting the energy as a function of filling.
So I'm plotting the. So this is the pair binding energy
on the right panel.
Oh, this is the quartet binding energy. So I'm doing n+2 plus.
So what's the compressibility of the superconductor?
Trying to remember. I don't remember off the top of my head. I can probably show you later the full energy curve. But
so is it finite or infinite?
Remains the same, dependent on density.
Well, actually, in this case, it should be finite and constant. I mean, I think because the many-body energy scales is number of pairs. So I think that's right.
And,
Yeah,
yeah,
we can also
just-
discuss the numerical.
Just one more thing. So,
Yeah.
so with that, we studied a somewhat similar model without the Berry curvature, just this kind of dispersion.
Right.
And one interesting thing there. So we didn't think about we just thought about the ferromagnet that you get there, and you actually get the spin stiffness even without Berry curvature, and the reason is the confinement in momentum space.
It's like the integration range, right?
Yes, yeah, precisely. So it's kind of a different mechanism to get stiffness, and I would think it's.
But the Magnon dispersion, was it like quadratic?
No,
it was weird.
Because of the singularity in the dispersion.
I
I think it was actually linear, and if you take something more smooth, it becomes quadratic.
So I think so at least what we can say is that if you, for instance, look at the dispersion of the Cooper pair, it does indeed look linear, and I think that's due to the sharp cutoff, right? And we can relax and see how that works. That's right.
When you get pairing for positive U and opposite sign of chirality, since this is apparently a first order effect in U, I would expect that those would appear as a product.
So you're saying positive U
and opposite chirality.
Well,
And I guess that it probably contradicts the worst by Trashcan.
I'm not so what
pretty much the same, but without the Trashcan, as far as I remember, right?
Our form factors are the same. What's your argument that that it should be?
This is the first order effect in U, in contrast to Kwan-Lattice.
Right.
And I would expect that what appears is the product of U and the chirality. So for positive U and opposite chirality, you would get a pairing too.
It's not clear that the spectrum is. I mean, it's funny here because, like, let's say for actually, no matter the sign of U, actually, right? If I look at the two-body problem, so on one hand, for say let's say beta is positive, right? Then all the positive chirality states, well, the either zero energy or negative, right? And all the negative chirality states are all exact zero energy states, right?
Exact zero.
Exact energy state. That's right. That's right. Right. However, that's statement about two particles, right? And our statements about this tower of states only apply. So I think one thing to be careful about is that, this is a restricted generating algebra. If you didn't have this constraint, then you could derive the full many-body spectrum. But once you go to many-body states, then we can only make statements about this particular state. Beyond that, we don't know. We can show as a ground state, but the excited states, it's not as trivial to derive the properties of.
I got the message. Thanks. We'll continue.
Yeah, sure. Sounds good.
Yeah. So I have maybe a follow-up about this stiffness. So we have a similar model, this hung et al, where we don't have the Trashcan. We regularize kind of the edge.
You do have a closed band.
Well, we have a closed band,
right,
yeah. And there we see the stiffness is just proportional to U, and the proportionality constant is something that's quantum geometric. And so it's saying that why don't you get something similar here?
I'm trying to remember the details here. I think either we made these calculations, but I think what happens is, so let's say we twist boundary conditions, right?
Yeah.
And in your case, you can just twist it right here. You sort of have a very singular action where you sort of shift it, right? And I think the change in energy was linear, but I'm not entirely sure. But that's why I hesitate to make.
So if you try just estimating it from the pair mass, you're saying the pair dispersion is not quadratic.
The pair dispersion is linear. That's right.
Okay.
In the infinite V limit.
Okay.
Fermi and then Andre and then Diner. So do you understand the transitions between the crystals?
Beyond being first order, I mean, we understand the wave functions of each phase, but they're first order.
Oh yeah, sorry. Same question as Lamas, but let me address the different questions. Suppose I look at this from the conventional BCS-like perspective. You have dispersionless fermions, right?
Dispersionless up to that, that's right.
Up to some after which energy is infinite. So you solve standard BCS equation, And instead of 1 over omega squared plus epsilon squared, you just get 1 over omega squared. So integration of a frequency, summation of frequency give you 1 over omega, which means the characteristic temperature should be proportional to U immediately. So from this perspective, you expect that all diagonal long-range order typical temperature will be proportional to U, probably times beta. But the opposite effect is fermionic self-energy, which is because fermions are dispersionless, it's also large, technically. So in some sense, my question, did you try to look from fermiology perspective into self-energy and to see maybe it vanishes because of special structure of form factors?
I see. I mean, I think we probably didn't think of that way just because it's a flat band, so we didn't know how to do a controlled calculation in case. But we haven't thought about perspective, but it may be worth thinking about it. Yeah.
On that note, let's thank the. It's at 6:35 tomorrow. You can come, give me the $20, then we'll give you the ticket. No much something. Yes, no, I the correct procedure
like this problem because they have we had that the zero
okay, that's weird. I can
the way the job can never be able to wait for.
Yeah, I understand.
Okay, I mean, it's not your fault. Yeah, I was confused because you mentioned the same, but yeah, it's okay.
Nice stuff. And also, yeah, he has the background. So, on the other hand, that's not engaged. That's maybe just yeah.
Here you don't think
well, at the very beginning, yes, but now it's a push plate on our guys, which sure you came up with So that changed towards the end of like last year. He started doing. I think we're gonna got more out of it.
Are you asking general question? Okay, okay. Good, good. Yeah, for general. Yeah, I know, we don't want to fund it.
Right.
Yeah.
To the other.
That actually